So I'm gonna start. I'm gonna work on the blind 75 problem, should I? And I'm not sure how good it's gonna be, but I just got this book and it arrived here yesterday. I started reading, I'm still on the beginning, so I didn't read much. But I think I'm gonna try a different strategy, which is gonna be to do these problems. Oh, let me open the list that I have here. I think I'm gonna do around 2 hours or so of these problems. And then after these 2 hours, I'm going to read the book, the pages that, not the pages, the chapters that have the data structures that I solved the problems. So if I did 3 problems, I'm going to look at the book for the tree section. And then I'm going to read the book. And then I'm going to go for 2 hours again. I think I'm going to do it like this and see how it goes. Because I think it might be better than to just try to do the list and then read the entire book after that. It might be better to go back and forth. That way, I think it's gonna help me retain more in my mind. And another thing is, I think I'm gonna try to finish this because the way that I like to do things is, and that I think it works, that I have been incorporating into other stuff as well, is first get a high level view and try to get as much breadth as possible, let's say. So study superficially a bunch of different topics to get a good idea of a good grasp of the general concepts and the way that everything works. And then after I do that, then I focus only on one or two things and try to become really good at them. And then I go back and forth between these two approaches. And I think that's the best way to optimize the way that I look at things. So I'm gonna try to do these problems as fast as possible, spending 30 minutes for each as before, and then look at the solution. And then after I do that, I think I'm gonna focus only on these topics here. This list is from this site that I saw before, and I didn't remember that I've seen, but they have this stuff where they created this ROI list for interviews. So this is pretty much the topics that have a highest return on investment for time spending studying. And I think I'm gonna, the smart approach is probably to focus on the ones that are easy to learn first and have a high ROI. So 2 pointers and graphs and trees pretty much. And then go on into the list. And I think that's what I'm gonna do. And I'm probably gonna focus, well, first on 2 pointers. 2 pointers doesn't seem to be, from what I've seen, it doesn't seem to be that difficult. So I'm gonna solve the problems in the list again. On the true list, the blind 75 and then 150 from this, starting from 2 pointers. And then I might, if I feel like I didn't learn much, I might go to the to LeetCode and search for more problems on 2 pointers. And then if I feel like I understood everything, or at least have a good enough understanding, then I'm gonna go to trees and then graphs, I think. Because graphs seems to be more difficult than trees. I haven't done any problems with graphs, but that's what people say, so. Yeah, so I'm gonna separate each 30 minutes for each here. Starting from this one. Yeah. And maybe I should go even faster, try 20 minutes or something like that. Because there's a lot of problems. So maybe, yeah, if I spend, so I have 35, no, 44. So 22 hours still, if I go half an hour each. And maybe that's fine. Okay, so if I feel like it's taking too long, I might decrease the timer. Given the roots of a binary search tree and an integer k, return the kth smallest value. Run index of all values of the node in the tree. One indexed. I don't know what that means. So the k is smallest value. So guys, I need to sort the tree based on value first. So we traverse through the tree, append the values in a list, sort the list at the end. And then, or I can just sort while I append. Okay, smallest value. Also, I'm supposed to count no values as well. Yeah, but then I need to return the node, that's the thing. I can just append the node based on the value. I'm trying to think if it matters if I try to go on the horizontal or vertical. But I think it doesn't matter that much. I think I'm gonna try to do the first approach that comes to my mind. And then I think about it after. I always forgot about this. Hmm. Because that should be values. So I wonder if I can map this based on the values. Yeah, but it doesn't make a lot of sense. It works here, but I don't think it's doing what I wanted it to do. Yeah. Maybe I can create a dictionary with. It's probably not good, but if I create a dictionary and then append the value, the node with the value, and then sort by the value. And let me just try to do that because why not? Then I think about a better way. And maybe it has to be an ordered dictionary. Sure. I keep thinking like this, but this is from the solutions of before that I saw with other problems. I don't think they do things like this. They always check if there's a node, but then for some reason I think it's because they do it differently. It doesn't break on because here is breaking because I have the node, but the node that left is no. And the way they do it doesn't give them that condition. Hmm. And now I'm thinking, can't I just do the order linked stuff on the root nodes and then sort the root node by value. It's probably not because it's not the same thing, I think. Yeah, now I remember this is based on value, and then if you wanna sort based on key, you do index 0. Hmm. And the easiest way I can think about is looping through the nodes and then the smallest value. Oh, it's a binary search tree. So maybe that's the thing. Because all the values in the left are gonna be. Yeah, so maybe I should be doing another function here. Miss the nodes. That's right. Yeah. I remember from a previous solution that you have to put boundaries here in return. Pass the roots, then float minus infinity, infinity. And then here, yeah, the solution was to validate if it's a tree or not. If it is a binary search tree or not. So maybe because I know that the smallest values are gonna be on the left, I should be going to the left first. But at the end of the day, it doesn't matter. Because either way, I think all this, both the depth first search and breadth first search go to the left first and then to the right. So let me think. Because the question is, how can I know the smallest value first? That's the problem here. If I could traverse to the left first and get the smallest value and then count from there, I think it would be easier. Maybe I can count how many nodes there are and then stop. Because the issue is the calculation then becomes harder because I'm not sure how to do it because if you start you're always starting at the root, so you don't know how many exist from the smallest to the root until you count all of them. So you can't do something like go to the left until the value is equal to k because then it's not necessarily true. Maybe I can use the queue and then append them each time. Append the minimum. Yeah, but it doesn't matter if it's the queue or not. Yeah, that's at least that's the only way I can think about it. But then probably I don't need this stuff here as well. But this is gonna return the, so I can do this. Then just append, right? Or actually, I don't need to check because the left is always gonna be lower. But that doesn't change anything. Maybe if I took the minimum each time between, and then I only append the that nodes. And maybe that's gonna sort the nodes. I need to find a way to sort the nodes. So I can loop to the final thing. Let me just print this and see what happens. But then I wonder if it's gonna append the value or. Oh yeah, I forgot to pass the key. Okay, I'm just gonna look at the solution.
Hey everyone, welcome back, and let's write some more LeetCode today. So today, let's solve kth smallest element in a binary search.
I'm gonna grab some tea before. Kinda exhausted today. Be right back.
Search tree. So we're given the root of a binary search tree and an integer k, and we want to return the kth smallest element in the binary search tree, right? And so remember, a binary search tree by definition means that it's in order, meaning that for, let's say, 3, everything in its left subtree is going to be less than 3, everything in its right subtree is going to be greater than 3. And so let's say k equals 1. That means we want the one smallest element in the binary search tree. So if you put all 4 of these elements in order, we get a 1, 2, 3, and 4. The smallest element is 1, so then we can return 1. And now, so your first thought with this problem might be that, okay, so in order, like you saw what I just did, right? I just took every element and put it in order and then took the kth element, right? And if k was 2, we would get the second element. If k was 3, we'd get the third element, right? So is there a way I can take this binary search tree and then put it into a sorted array or something? And the answer is yes, right? Because binary search tree means that if we traverse this tree in order and then take each element and then put it into an array, then we've basically solved this problem. So for example, we start at the root, but we don't visit the value yet, right? We go to the left child, right? And then we see, okay, it doesn't have a left subtree, right? It doesn't have any left child. So then we visit 1. By that, I mean we basically put it inside of our array. Then we go to its right subtree. We see, okay, 2. We add 2 to the array. And of course, since we know k is 1, we could actually stop here once we visited the 1, but we could also continue to add elements. So then we'd pop back up to the 3, add the 3, and then we go to the right child and then see the 4 and add the 4. And so you know that writing an in-order traversal for a binary search tree recursively is pretty easy, right? But I'm going to show you how to do it iteratively, which you might not know yet, but it's actually pretty similar to doing the recursive solution. So you saw how the recursive solution works, right? Let's say we visit 1, then we go to its right child, right? We visit 1, and then we visit 2, and then we end up having to pop back up to the 3, right? So to pop back up here, we know the recursive call will eventually come back like with the call stack, right? That's how function calls or method calls work. But if we're doing it iteratively, not recursively, right? Then we need a stack to contain the previous nodes that we need to pop back up to. So I'm going to show you how to do this problem with a stack iteratively. So let's say that this is our stack. So iteratively, we start at the root, right? And we're not going to visit this node yet, right? So we're not going to count it as a kth value yet because we want to go through everything in the left subtree first. So next, I'm just going to keep going as far left as I can. So I'm going to go to this node, right? It's left child. But before I go here, I'm going to add the 3 to the stack because we know we want to pop back up to this 3 when we're done traversing the left subtree. So now I'm at the 1. I'm going to go to its left child, right? But we see it's null, right? But before I go to null, I'm going to add 1 to the stack. But once we reach a null case, that means it's time for us to pop back up and go back up to the previous node. And we know that because we just look at the top of our stack. So we take this 1, we remove the 1. And so basically when we remove an element from the stack, that means we're processing it or visiting it. And we see k is equal to 1. This is the first value that we just visited, right? So then it must be the result. So the 1 that we just popped is going to be the output, right? But let's say that it wasn't. Let's just continue the iterative solution just so you can kind of understand how it works. So now I'm at the 1, right? We just processed the 1. We don't have to ever consider it again. So I'm just going to cross it out. But now once we pop up, right, we visit a node, then we want to go to its right child. Only after we visit the node, after that, do we want to go to its right subtree, right? Because remember, we're trying to do this in order. So with 3 still remaining in the stack, we're going to go to 2, right? So now we're going to add 2 to the stack. And now I'm going to go to the left child of 2, right? We know it's null. So then we're allowed to pop back up, right? So we're going to go to the 2. It's because it's at the top of our stack, right? So the 2 is at the top of our stack. So now we're going to pop the 2 off. So meaning we're processing the node 2, we're visiting it, so we can cross it out now. And now I'm going to go to its right subtree, which is also now null, right? Because now that we process 2, we're allowed to go to its right subtree, but we see that it's null. So since it's null, that means we pop again from our stack, right? So we're done with this null, but conveniently for us, we have a 3 at the top of our stack. We crossed these 2 values out. So now we're going to automatically go back up here. So we pop the 3. So now it's time to process the 3, right? We process it, we look at it, we visit it, whatever you want to call it. And after we visit it, then we're allowed to go to the right subtree. So now we're at 4. So we add 4 to our stack. And you basically know what's going to happen now. We're going to try to go to the left subtree, but it's going to be null. So we pop from the stack. So we process 4. Then we try going to the right subtree. It's also null. So now we look at our stack, right? We're going to pop again from our stack, but our stack is empty, right? So that's how you know the algorithm is done. We visited every node that we needed to. And if you were actually keeping track and you noticed the order that we popped the elements in, so basically the first element we popped from our stack was a 1, if you were paying attention. After that, we did a 2, right? We popped the 2, and then we went back up to the 3, we popped the 3, and then finally we visited the 4, right? So even though we did it iteratively, we visited the elements exactly in order. So it's surprisingly, the iterative solution is not quite as hard as you might expect. Let me show you the code for it now. So I'm going to declare a variable n to basically tell us the number of elements that we visited from our tree. Once n equals k, that's how you know we visited the element that we wanted to, and then we can return that value. And remember, I'm also going to have a stack, which is going to help us because we need it because we're doing this iteratively. So I'm also going to have actually a pointer cur. It's going to initially point at the root. It's basically going to tell us what node that we're currently visiting or at the node that we're currently at. And so I'm going to have a while loop. Basically, while current is not null and the stack is non-empty, we're going to continue traversing our binary tree, right? That makes sense so far. And remember, the first thing we want to do, let's say we're at cur, what are we going to do? While current is not null, we're just going to keep going left, right? Remember, we want to go through every node in the left subtree before we visit the current node. So while current is not null, we're going to set current equal to current.left. But remember, before we do that, we have to go back up to current after we're done processing current.left. So before I do that, I'm going to take the stack and add current to it. And so when this loop is done executing, that means current is at null. So that means we went too far. And that means we have to pop the last element that we added to our stack. So actually stack pop. We're popping the most recently added value from our stack. And we're going to set it to cur. So now that we popped this element cur, that means we're processing it. So what we can do is actually update our n value, that means we just visited another node, so we can increment n by 1. And if n happens to be equal to k, that means the current node that we just processed is the value we're looking for.
Yeah, it makes so much sense. Don't know how I didn't think about that. It's because you're going until the end, and then once you get to the beginning, which is the left side, then you can pop and start again.
Remember, we are looking
I think
for
I
the
get it now.
kth smallest element. So if that's true, then we can just return current.value and we're done. We don't have to visit any extra elements. But what happens if this is not the case? Well, we just processed current, right? That means that we're allowed to now go to its right subtree. So we can actually update current now and set it to current.right. And so what's going to happen now? Well, the loop is going to actually go back up. If current.right is non-null or the stack is non-null, then we're going to start our loop. And for that node, we're going to keep going left as much as we can. Maybe it doesn't have a left subtree, so then this part is not going to execute, and then we're going to end up just popping again from our stack. And conveniently for us in this problem, we're guaranteed to have at least k nodes in our tree, so this is actually always going to execute. We're not going to end up exiting this while loop. So we actually don't even need a return statement over here. And this actually is the entire code. Let me just run it for you to prove that it works. And as you can see, it's, according to this, not pretty efficient, but I'm pretty sure if I ran it again, I would get a much more efficient time. But you can see this is the iterative solution. It's roughly the same time complexity as the recursive solution. And surprisingly, it's not that much code, right? Like, you might expect the iterative solution to be more complex, but we're actually not doing anything fancy. We're just going as far left as we possibly can, adding the values to the stack, and then popping from the right when we need to. So I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Yeah, so like I said before, I'm just gonna go to the next one. I think I'm not gonna concern myself with trying to solve it. I think what I'm gonna do after I do all this list, the problems in this list, I'm gonna, because I think I already have somewhat of an idea of the things that I'm struggling with to understand. So after I do that, I think I'm gonna scratch the 30 minutes for a problem, and then I'm gonna work on those problems with the book, and I'm gonna try to improve on my understanding of the things that are kind of difficult for me to think about, like the recursion and stack. So it should be, and integrating that with the problems. And for now, I'm just gonna kind of get this sense of the way that he does things and the standard algorithms and ways to do things. And then I'll do that. Construct binary tree from pre-order and in-order traversal. Given show integer arrays, pre-order and in-order, where pre-order is the pre-order traversal of a binary tree, and in-order is the in-order traversal of the same tree. Construct and return the binary tree. Yeah, I don't have any idea what that means. Pre-order traversal. Okay, so pre-order 3, 9, 20, 15 sound. In order 9, 3, 27. So pre-order is a zigzag on horizontal, and in order is zigzag on vertical, I think. Damn, this is a lot more difficult. Seems to be a lot more difficult than the previous one. Also, I have true. I have the true arrays of integers. Huh. So maybe it's not that hard actually. And the biggest problem is the no values here. Can't I separate them into tuples? Because each level is gonna be but then I have to think about how I'm gonna make the each node. Because I'm thinking about using the pre-order one, and then dividing this, removing the first element and dividing by multiples of 2 based on the levels, and then creating the nodes that way, but it's probably not the best idea. If they're giving both, I assume that the best way is probably gonna involve mixing them, but I'm not sure how exactly. So this one is going like this, and this one is going like this. Yeah, I have no idea. Do you mean here? I don't have any idea how to do this. The issue is I can't even think about a good way to start because it's kind of confusing to think about the way that it jumps on here. Has 3, 9, 20, and then goes to the bottom of the 9 one, and then to 20. But how am I gonna connect this one to these ones? That's the question. Also doesn't make sense in my mind to combine the two. I can only think about ideas with the pre-order, but using both of them, it doesn't make a lot of sense to me. Because this one is gonna depend heavily on how high the tree is. So you can go from any place to the top and then down. Start to create a logic based on that. The other one I think makes more sense because you're going horizontally, so you can. I'm trying to think about ways to divide the list based on the on multiples of 2, and then padding the list with no values. But that also is it seems like it can't be the best approach because they're giving me the two things here. It's just really confusing to think about it. What if I saw pre-order and think about how to apply it if there are more nodes? Then it's your first elements. So pre-order 3920. Then think about how to apply it if there are more nodes. Whether it's your first element in pre-order is mid element in order. First element in pre-order is mid element. Is it though? Because first element in pre-order is mid element in order. Because here is 3 and here is the second one. It doesn't seem like depends on how many nodes exist on each side. I'm trying to capture the essence of this, but it doesn't make any sense in my mind. I'm obviously missing something. And I don't want to just solve or try to solve based on the multiples of 2 because I feel like even if I can make it work, it doesn't make sense in the way that I'm thinking about it. So it's probably not the best approach. But if I try to mix both, I'm still stuck because I can't see the patterns there. And probably, if I suspect, it has something to do with the way that pre-order and in-order are supposed to, because I don't understand how pre-order and in-order algorithms work. So there's probably something to do with the way that these algorithms work, that you can combine both of them to build the tree. It's like reverse engineering the thing. But and I could do pre-order 0 is equal to root, but that doesn't make sense for me. I think I can put any value as well, but I'm not sure. Oh, the value is supposed to be the value in the list, so I'm getting the wrong way. Oops. Another 0. And that's the other thing about it, is that I'm not sure if I should be creating the objects as well. Probably because I'm supposed to return a tree, not a list. which is the other thing that I don't know what to do. Because depending on which node it is, I'm gonna have to create the object differently as well. Like this. Mm. Oh, so I don't need to put the values as I create. Oh, because they're gonna be done by default. You're right. Hmm. So obviously I can use the logic that I was talking about, but I don't think that makes sense. I can make root left because the preorder one and the right preorder true, but then in the next call is not gonna work. And I probably should modify the lists as well as when I call the left and right. And the in order stuff that doesn't make any sense to me. I guess I can think about the indexes as shrinking the tree and they're in order. So it starts at the left and then goes to the top and then goes to the bottom again. But then I'm not sure if 9 had a right node here, would it go to the 9? Probably. So if it was 12 here or something like that. I have no idea. Also, if I call recursively here, there's probably other conditions that I need to put here because it doesn't make sense to just pass the list. Because that this way I'm always making the root equal to the unless I change the list as well. Because then I'm getting the 0 index. So maybe I should pop. You should modify each list, but each time before I call this again, but doesn't that uh, isn't that gonna fix the list by the same index always? So unless I do it with root, pre-order roots or roots. No, actually, that should be. No, it's probably like this. I just don't get the logic. I'm having a hard time thinking about. It's just confusing as fuck. You need to find what the slicing should be. But yeah, instead of popping. Because I get the idea of what they're trying to tell me to do. Like the problem. Because one goes zigzag horizontally, the other vertically, so you have to combine both to create, but it's too confusing. So maybe every element of the in order has to be the parent node, and the left and right ones are the in order one. And the in order is the parent, and the pre-order is the left and right. But that wouldn't make sense because then it goes from 3 to 15. So 15 doesn't have any nodes. Yeah, I'm just gonna look at the solution.
Hey everyone, welcome back, and let's
Obviously,
write some more
I'm
neat
not
code
gonna
today. So
copy
today let's
it,
solve a pretty
but
fun problem. Construct a binary tree from a pre-order and in-order traversal. So we're actually given two integer arrays representing one, the pre-order traversal, and two, the in-order traversal of a binary tree. And our goal is to take these two traversals and the orderings of those nodes and then reconstruct basically the original binary tree that the traversals are from. And it is technically possible. These two traversals have all the information we need. We just need to take that information and then deconstruct it and then reconstruct this binary tree from those. So just to verify it, let's go through this tree and actually do the pre-order traversal first of all. So first, we know pre-order traversal is you start at the root and then you process the current node, then you do the left subtree, then you do the right subtree, right? So let's just do the pre-order traversal. So we're starting at the root. We do the root node first. That's how pre-order works. So then we get a 3. Next, we're going to go to the left subtree and then do pre-order traversal on that left subtree. We see 9, right? So we're going to add 9 to our pre-order traversal, and it doesn't have any children, so we're actually done with 9. We're done with 3. Now it's time to do the right subtree in pre-order traversal. So we start at 20, add 20 to our pre-order, go left, we see 15, add 15 to the pre-order. 15 doesn't have any children. Now we go to the right subtree, 7, so add 7, it's our last node, to the pre-order traversal, right? And this actually, take a look at this, take a look at all the values, it matches exactly with the input, so this is the pre-order traversal. Now let's just validate the in-order traversal as well. In-order traversal is we start at the root, right? We take care of the entire left subtree first, then we take care of the root node, and then we take care of the right subtree with in-order traversal. That's the general order, so let's validate the in-order traversal of this tree. So we're starting at 1, or we're starting at the root 3, but we're not going to add 3 yet. First, we're going to do the left subtree. We see we have a 9. The 9 does not have any left or right children, so now we can add that 9 to our in-order traversal. Remember, we're doing this in order, left to right. We go back up to the root. Now we can process the root. We can take 3 and add it to the in-order traversal, and now we're going to do the entire right subtree. So we get to 20, but we're going to wait for 20. We're going to first do the left subtree, 15. 15 is the only value here, so it doesn't have any children. Add 15 to the in-order traversal. Now we can add 20 because we've done the left subtree. 20 is added, and then last we go to the right subtree, only one value, 7. Let's add that 7 to our in-order traversal. Now let's take a look at these 5 values. Notice how they are the exact same 5 values in the exact same order as that in-order traversal that we were given. So we can see that
what they gave us was correct, but now the question remains, how can we actually take these two arrays, these two traversals, and construct this tree? Well, it's definitely possible. Let me show you how to do that right now. So I just want to let you know that there's actually two main facts that we're going to be using to construct this tree. So the first fact is that the first value in pre-order traversal is always going to be the root, right? We remember when we do pre-order traversal, right, we're always processing the root first. So if I was taking the pre-order traversal that we're given, right, we remember this is the pre-order traversal that we're given. The first value in pre-order traversal is always going to be the root. So this is the first value 3. It's guaranteed to be the root because that's how pre-order traversal works. The first value in pre-order traversal is always the root node. Now we don't know about the rest of these, right? But we can recursively construct now the left subtree and the right subtree, right? We're done with this 3, right? Now our goal is to reconstruct the left subtree. Hey, lucky for us, the first value here is always going to be the root of the left subtree, right? Because that's how pre-order traversal works, right? So that's one thing that we're going to use. The first value is always going to be the root, and then we can take the sublist, right? We can remove the 3. We don't need to look at it anymore. Then we take the sublist, and then basically we're going to do this recursively. That's what I'm telling you. Okay, we can construct the root, but we need more information than that, right? And then let's say we're done looking at this 3 now. I want to take this array, right? And I want to know which values are going to go in the left subtree and which are going to go in the right subtree. From looking at the actual tree itself, we know the answer, right? We know that this is where we're going to cut our list, right? The 9 is going in the left subtree, right? These 3 values are going in the right subtree. But how can we determine that? Well, that's what we need our in-order traversal array for. Okay, so now let's take a look at the input array we're given for the in-order traversal. And by the way, let me just mention that every value
Yeah, this part I'm gonna go slower because that was I was thinking about that, but I couldn't find a way to connect both of them.
in the traversal is guaranteed to be unique. That's true for both of the traversals, the in-order and the pre-order. Every value is going to be unique because every value in the tree is going to be unique. But okay, so far we know that this first value 3 is going to be the root, right? So now let's find 3, right? We know 3 is the root, right? So we removed it from our first list basically, right? But now let's find it in our in-order list. We find it's right over here. 3 is in this index, right? So
Physics
we
slow
know we
motion.
don't need this 3 anymore, right? We already created that node. But so now what does this in-order array tell us? Notice how this is convenient for us. Every value to the left of the 3 that we just created the root from, every value over here, which is only 9, is going to go in the left subtree, and every value to the right of 3 is going to go in the right subtree. That's really convenient for us. Why is this the case? Because that's basically the purpose of in-order traversal, right? It guarantees that we're going to go through the tree in order, right? From left to right, basically. Right? So if we see the 3 here, and this is the position in the array, we know everything here is going to be in the left subtree, everything here is going to be in the right subtree. That's what it tells us. This is really convenient for us because we can count it, right? We can see there's exactly one value that's going to go in the left subtree, and there's exactly 3 values that are going to go in the right subtree. So what we can do is we can take the remainder of the pre-order array and then partition it, right?
What I still don't understand is what if you have 12 here or another value below 9? Let's say you have 2 values in the left and then 1 value to the right of 9. It's gonna start at the lower left value and then it's gonna go to 3. But then isn't it going to go for the right of the value in the 9 instead of going to 15? So how do you know if it is gonna be separating like that all the time?
Partition it over here because we know 1 value is going to go in the left subtree and 3 values are going to go in the right subtree. So that's what we're doing, and we're going to continue this, right? So now let's and by the way, in the code, we're going to do this recursively. Let's create the left subtree. We know that, okay, this is the in-order portion, right? And this is how we're going to partition it from pre-order, right? We see this is the array to create the left subtree. The thing here is, notice how this is size 1, right? There's only 1 value here and there's only 1 value here, right? That tells us that the subtree we're creating is only going to have 1 node in it, right? So 9 is the only node in the left subtree. So we're going to create that node, put the value there, and now we're basically done with this left subtree, obviously, because there's no more there's no more nodes left in this general area, right? These values are reserved for the right subtree. This is reserved for the right subtree. Okay, so now we're looking at the pre-order portion, right? There's 3 values, just like in the in-order portion. And remember, how are we going to create the root node of this subtree now? We always take the first value in pre-order traversal. It's 20, right? The value is 20. So we're going to take this value 20. We don't need it anymore because we're going to create a node from that value. And so now we need to know which values are going to go in the left subtree and which are going to go in the right subtree. We know by finding 20, right? 20 is the value. Let's find 20 in our in-order traversal. It's over here. By the way, in the code, I'm going to be calling the index of this mid. So M for mid. We find the index of 20, right? We know we don't need 20 anymore, so we can get rid of it, right? We see that there's one value on the left of 20, and there's one value on the right of 20. This tells us that one value is going to go in the left subtree and one value is going to go in the right subtree, right? Just like we have over here. So now let's construct that left subtree. We know it's going to be exactly size 1 from looking over here. So we take this 15, right? Now our job is to recursively create the left subtree. We're going to take this 15 since it's the first value in the subarray for pre-order, right? We know that it's going to be the root of the current subtree we're at. So let's get rid of this 15. Let's create that node, right? 15 over here is going to be a node. And there's no more values left in this subtree because we know it's only going to be size 1. Okay, now we're creating the right subtree. We know that there's only one value in the right subtree from looking over here. And since there's only one value left in general, it's a 7. We can make a node from it. And then we're done. We know we're done because we've basically gotten rid of every single value in our arrays, pre-order and in order. So using these two arrays, we were able to create our tree correctly. And let me summarize what we're actually doing. We're not doing a lot. We don't need a ton of information. Remember, the first value in pre-order, the pre-order array is always going to be the root, right? That's just how it works. And then once we take that value, create a node from it, and then when we try to look that value up in order traversal, right? Then we can get some subarrays, right? We can take the length of the left and right subarray. So the right subarray is 3 and the left subarray is 1 node. Now these counts 1 and 3, they tell us how to partition the pre-order traversal. So take a look at the pre-order traversal. 1 tells us that we're going to cut over here because this needs to be size 1, this needs to be size 3. And then from this subarray with only one value, we are going to recursively run the algorithm to create this left subtree. And with this subarray, we're going to recursively run the algorithm to create this subtree. And we're just going to continuously repeat that process until we get to our base cases and until we're finished with every single node that we need to create. So now let me actually show you the code. It's actually very short, less than 10 lines. Okay, so as I mentioned, this is a recursive algorithm. So we always want to start with the base case, and the base case is going to be, what if we don't have any nodes to traverse through the two arrays that we're given? That means we can return null, or basically we don't have to create a tree. So if pre-order is empty,
I think I'm gonna remove the camera until it's night here so I can turn on the lights, because I don't wanna open the window and have a reflection. So
or in order is empty, then we can return null. We have no values, so we don't need to create a tree. We can return null. Otherwise, we're going to create a tree node, right? And what's the value of that tree node going to be? Well, it's going to be the first value that happens to be in the pre-order array, just like I showed you, right? Always going to be the first value, so it's always going to be index of 0. And then whatever that value was, we want to find the position of it in the in-order array. So in-order.index, so we want the index of that value, pre-order of 0. and we're going to get it in mid. Now this is the part where we're going to build the subtree. So root.left, let's create the left subtree, and we're going to do this recursively as I mentioned. So self.build tree, we're calling the function that we're inside of. And the convenient part about Python is we can do sublists, so that's going to cut down our code quite a bit. So we need to pass in the new pre-order and in-order arrays, or the subarrays more likely. So pre-order, what are we going to pass in for the left subtree of pre-order? Well, mid tells us how many...
I think now I understand the hints you're giving me there. It's because the middle is always going to be the same index there from the first one in the pre-order. And that's the stuff that I wasn't understanding, because I thought that depending on the tree, you might change the index of the middle in the in-order traversal. Because I don't understand how the in-order goes from one node to the next. But it's still, even after watching this, it's still difficult for me to think about it. Because after you do that, you still have to think about how the recursion is gonna affect both lists. It's kind of difficult to think about it.
Nodes we want, the index of basically the value of mid tells us how many nodes we want in the left subtree. So what I'm going to do is for pre-order, we're going to start at index 1. We're basically skipping the 0 index because we already just created a node for the 0 index. We're starting at index 1, going all the way up until mid plus 1 in Python. This mid plus 1 is non-inclusive, so this subarray is really just a pre-order from index 1 to mid. So that's what we're doing, and we're going to pass in the in-order portion that we need as well, and that's just going to be from the beginning up until mid, but not including mid, right? This probably makes more sense if you go back and look at the picture, but basically we're just creating the appropriate sublists that we need to create the left subtree. We're going to do basically the exact same thing with the right subtree. And I would encourage you to draw this out yourself to basically reinforce what you're learning or watching me do right now. So to build the right subtree, we need every value after this sublist, right? So we can just say starting at index mid plus 1, going until the end of the list. That's how you do it in Python. We're starting at mid plus 1 and going until the end of that sublist, just like I showed in the picture. And for in order, we can actually do the exact same thing. We want every node to the right of mid in order, right? From our in order array, we want every value to the right of this index mid. So we can do that with mid plus 1. Starting at mid plus 1 and then going until the end of the array. So now let me close this function. And so this is literally all you have to do. The reason it's so easy is mainly because I'm using Python, but you could do this code without Python. It would probably just be a couple extra lines. You might need to pass in a couple extra parameters into this build tree function, basically just these indices that I'm doing. You might not be able to create sublists, but you can at least pass these indices into your functions in Java and other languages. So with that, we have actually created our tree. So the only thing left for us to do is return that tree. So with that being said, this is the final solution. It's probably less code than you would have predicted, but the problem is a little tricky, but it's kind of enjoyable, at least in my opinion. So I hope that this was helpful. If you enjoyed, please like and subscribe.
So I think I got the gist of it, the main logic. I should definitely spend more time on this, but like I said before, I want to go fast through these ones. I think that's the one that I just did until I finish the list. Then once I finish the list, I'm going to focus more on these ones. And I'm not gonna do just LeetCode challenges. I'm gonna watch videos as well, probably. Yeah. Because before I was thinking about doing the list several times in a row, but now I'm thinking that's probably better because now I know the stuff that I don't understand really well. So it's probably better to spend time, a bunch of time trying to understand those things. And only then attempting to do the problems again. I mean, can only imagine how hard it's gonna be for the graph stuff. If this is already hard for me. A path is binary tree maximum path sum. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes In the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the node's values in the path. Given the root of a binary tree, return the maximum path sum of any known empty path. Damn. The optimal path is 2, 2, 1, 2, 3. With a path sum of 2 plus 1 plus 3 equals 6. Okay. It's 15, 20, 7 with a path sum. So pretty much I have to return the sum. So I need to return the output of the sum of the most optimal path. So I guess the challenge here is that I can only navigate through one node at a time. So I can't just go through all of them and then find the sum. Find the highest sum, I think. Because the path matters. I think I'm gonna put some music as well while I think about this stuff. Because since I don't know how to do all these problems, I think even probably all the other ones I assume they're gonna be very hard as well. So I'm gonna be thinking most of the time and probably not coding at all. Since I don't know what to do. I assume I need to have a sum here, or a variable to store the sum of values. And then I need to think about how to traverse the tree. So maybe, yeah, I think there is depth first search and the breadth first search. Those are the two methods, I think. So maybe I should try to implement both of them. But then how do I get the sum? That's the thing. Because if I just store the values in a variable, it doesn't make sense. Because then it would be like summing here all of this. It doesn't. How I'm gonna know which node to stop this sum? That's the thing. Yeah, this is hard.
Do you think of my heart? Do you have the time? Do you think of my heart? Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a
What I'm stuck at is trying to think about a way to set the boundaries. That's the biggest problem. I'm not sure if I remember as well how to navigate, how to do the depth first search. I think it's something like this, or just call recursively, and then to traverse through the breadth first search to do the queue stuff. But I'm not 100% sure. I think so far those are the two key things I need to get down first. After I'm done with all these problems, I need to study more the breadth first search and depth first search until I really understand off the top of my head how to do them and in which direction they are going first. Because it's hard for me to think about what nodes are being visited, and it feels like to solve these problems I need to because that's just the if I don't understand which nodes are being visited, then I can think about the other logic that is necessary to do whatever they are asking for. Because I'm not 100% sure which way it's gonna go.
Stay still until they find it out.
Is there a way to get all the possible combinations of some? The issue is that I have to maintain the path. I need to do a flow of if-else statements to maintain the path conditions for the sum.
Slow down the sunrise and keep it up. Put a cold in my bones, what spirit low. And your mind is beautiful, child. Stay still until they find it out. Smell of roses in the air. 19th century atmosphere. Where is just my feet are bed. The 19th century atmosphere.
Yeah, and I don't think I can go back. Just if I start at -10, I have to go through 15. Can't go through 15 and then back to 20.
Alright, I'm ready now. I ain't gonna fall back now, no. Alright, I'm take it on me, baby. Alright, I ever ask, are you gonna be my lover? Tonight, I take it with me. What if I left, then it made no sense? And you tell your friends, and they hold your hands, baby, never mind. What if I left, then it made no sense? And you tell your friends, and they hold your hands, baby, never mind. What if I left, then it made no sense? And you tell your friends, and they hold your hands, baby, never mind. What if I left, then it made no sense? And you tell your friends, and they hold your hands, baby, never mind. Alright, I'm ready now. I ain't gonna stop right now. Alright, I take it on me, ooh baby. Alright, I ever ask, do you wanna see my fire? Tonight, take it with me, What if I left, then it made no sense? And you tell your friends, and they hold your hands, baby, never mind. What if I left, then it made no sense? And you tell your friends, and they hold your hands, baby, never mind.
Maybe you should just try to get the sum of from left to right. Which one? And then I think about going to the depth. Let me try to do that. I think I'll definitely not be able to solve this, but maybe I can figure out an easier.
Drifting, try to sleep the time away. I'll wait for you. Hopeless, drifting, try to
I
sleep
know
the
that's not
time
gonna
away.
be.
I'll wait for you. Hopeless, drifting, try to sleep the time away. I'll wait for you.
Tell me where you're going. If you love me, then somewhere. I've just about it.
And then I need to have maybe
If you love me, then
I'll do this equals C
tell me where you're going.
minus equals max.
Somewhere. I've just about it up the list. If you love me, then somewhere. Oh, tell me where you're going. If you love me, then somewhere. I've just about it up the list. If you love me, then somewhere.
I'm also gonna be missing the null value nodes, but I don't think that matters that much. And then I need to make C equals 0.
Tell me where you're going. If you love me, then somewhere.
Oh, I didn't make the.
About it up the list.
I forgot about this.
Hopeless, sleep the time away. I'll wait for you. Hopeless, drifting, trying to sleep the time away. I'll wait for you. Hopeless, drifting, trying to sleep the time away. I'll wait for you. Hopeless, drifting, trying to sleep the time away. I'll wait for you.
Oh, tell me where you're going. If you love me, then show it. I'm just about it up the list. If you love me, then show it. Oh, tell me where you're going. If you love
Okay, so yeah, but that's, I need a better test case. That's the problem. Because I know for sure this is not gonna work.
I'll wait for you.
So maybe if I did this, but I'm not really sure still how to mix both depth first search and breadth first search as still. Because maybe I could use this with recursion to get longer paths. But there's still the issue as well of how I'm gonna decide when I stop counting. Because in this case, for example, I can go to 9 until 15. But then, obviously, it would be better if I stop at 10, minus 10, and then continued searching on 20. I wonder if this is a valid path as well, from 9 until 15. Because that one would combine both horizontal and vertical movements. Because if I could separate because yeah, if I could only count paths that are either vertical, but even then, I think it's still a problem in this question of how to decide when to stop counting the path and start again. That's the biggest thing. Because what I'm thinking about is if I could separate vertical and horizontal, I can maybe do a recursive call in the beginning to traverse in the vertical way, and then do the same thing with the result here, where I'm just setting the values. And then after that I traverse on the horizontal way and then compare both of them and return the highest. But the biggest thing that I'm stuck at is trying to understand or trying to think about what kind of logic I can implement to stop counting the rounds and begin again. That's the main issue. There's also the problem if you have to mix both of them. It's even harder. Yeah, and just doing all counts possible and returning the highest doesn't seem reasonable. There's too many paths to count. Let's see how much time I have left. 5 minutes. I'm still gonna spend time trying to think about it, even though I know I won't be able to solve. Just to force myself to think about what possible solutions can exist, and so I can understand what parts of my thinking I'm missing. The way that I'm approaching this, the logic that I'm trying to implement. In the previous one, I was missing the understanding of how the nodes how the paths are working. So, and I think doing this allows me to understand what I have to work on. So I become better at these problems. I think I'll be right back and then probably look at the solution when I'm back. Right, I'm back. Let me look.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve binary tree maximum path sum. And yes, this is another problem from the blind 75 LeetCode list. So this is a list of 75 common LeetCode questions, and today we're going to be solving this tree question, binary tree maximum path sum. The link to this spreadsheet will be in the description if you do want to take a look. And I think I've almost done all of the problems that I wanted to do from this list, nearly all of them so far. So a path is defined in a binary tree as being a sequence of nodes where each pair of adjacent nodes in the sequence has a edge connecting them, and a node can only appear in the sequence at most once. And the path sum of that path is defined as being the sum of all the nodes' values in that path. So for example, in this example, we're given a tree, and the path is basically going like this, right? You see how, we have a node, we go here, and then we go here, right? This counts as a path, right? Even though from here we're technically splitting, we're going left and right, this is still a sequence of nodes, right? It could be read like in any direction, but it's still like a sequence. And then when you take that path, you basically get 1 plus 2 plus 3, so that's going to be the output. Now, of course, in this problem, we can actually have negative values. So for example, this 2 could be -2. So then what would be the maximum path sum then? Well, we don't want to add negative values. That won't increase our total. So in this case, we're going to go from here to here, right? This is going to be our path, 1 plus 3, and then we would return 4. Now, what happens if this -1, this value was a -1 instead, right? Now, we could just take 3 by itself, that counts as a path, or we could take 2 by itself, that counts as a path, or we could still take that same path, which would give us 2 minus 1 plus 3, which gives us 4, and that is actually the max once again. So it's possible that negative values could still be included in the output. So you might think, well, what if we have a tree of all positive values like this one? Can we just take every single node, like basically like this, and call it a path and just add every value together? Well, no. And the reason is because if we had this structure, right, this isn't really a path, because how would you traverse it, right? We could start here, then go this way, then go down, but then here we have to make a split. We can't go in 2 directions at once. That doesn't count as a path. So basically what we realize is, as we look at this example, is that if we're starting at a node, we can only split once, right? Like if we're here, we can split in 2 directions, right? We can include a path from here, from the left side, and then we can also go here, right? And if we get to this portion, right, we already had a split up above, so we can't split twice, right? Because then it's no longer a path. So we can only choose one of these nodes. We would obviously choose the bigger one, that's a 5. Right, so take a look. What would the sum be if we ended up splitting from here? This is obviously the max we could create. What is the total? It's 1 plus 2 plus 3 plus 5, which is going to be 11. Now, we're going to try it multiple ways, right? It's possible maybe there could be a split over here. Of course, this doesn't have any children, so the most we could get doing that would just be a 2. But what about over here? What if we ended up splitting from here? So we took the left and the right from here. We'd get a 4 and we'd get a 5. Now, if we did do that, notice how this is going to be the topmost node. So whenever we split from a node, we can't really get any of its parents or anything like that. So in this case, what is the sum of this path? Well, it's going to be 4 plus 3 plus 5, which is going to give us 12. 12 is greater than the 11 that we had previously, so this is going to be the max path sum. So you can tell that a brute force approach would be for every single node, consider it being the topmost node, and then from the left subtree, basically find what's the maximum path we could create in the left subtree if we never split. So we can't include both left and right, and then do the same for the right side, right? And if we sort of do it recursively, we can eliminate repeated work. So suppose we're given that same tree. We're going to start at the root like normal, right? So from here, we want to know what's the max path sum we could do from here if we split from this position, right, going left and right. Now, Why start at the root when we could solve the subproblem first and possibly use that subproblem in the result at the root position? So we're going to leverage that idea, a depth first search idea, just like usual with tree problems. And using that, we're going to end up getting a linear time solution, and it's just going to depend on the return value of our recursive function. So we're going to start at the root. And now we're going to go left, right? We want to know what's the maximum path we can get from the left subtree if we never end up splitting. So in this case, it's pretty simple because it doesn't have a left child or a right child, right? So we don't even end up having to split, and we get a sum of 2 from this spot, right? And even if we were splitting from here, we would get a total of 2 so far. So what we'll say is, so far the max path we've gotten so far is 2, right? Now, we still want to know what's the max we can get from this position, so what we're going to do is now go to the right tree. So recursively, now we're going to ask the question down here, what's the max path sum we can get if we ran it through this position and we ended up splitting left and right? And by the way, our result so far is going to be 2. That's the maximum path so far that we've gotten. So from here, we're gonna, since we're trying to again find what's the max we can get splitting from here, we're gonna go recursive, and we're gonna do that for the left subtree and the right subtree. So we're getting that same base case here, right? With this left subtree, if we tried to split from here, the max path we'd get is 4 because it doesn't even have any children, right? So let's keep track of that. The max path we could get from here is 4. Now, if we didn't split here, we'd also get that same value of 4. And that's what I'm marking here. Next to each node, I'm marking what's the max we could have gotten if we did not split. I know it's a little confusing, and it'll make more sense once I actually finish the rest of this example. And so from over here, now we do have what's the max we'd get from the left path without splitting. It's 4, but now we just want to do that for the right side. Once again, it's that same base case, right? So what's the max we could get running through here if we never split? It would be 5. It doesn't have any children, so we couldn't split even if we wanted to. So now we're at this node once again. We have computed the left and right subproblems. Now from this node, we're going to be computing 2 different values. By the way, our result right now would actually be 5 because that's what we've gotten so far. So from this position, I'm computing 2 values. I want to know what's the maximum sum we could get with a path running from here if we are allowed to split. So we are allowed to go right and we are allowed to go left. So what would the total of that be? Well, of course, we would just take, okay, what's the max we could get from the left subtree without splitting, right? Because we can't split again. If we already split up here, we don't want to split again here. So what's the max we could get from here if we never split? Well, it would be 4, right? And once again, what's the max we could get from here if we never split? It would be 5. So up here, I'm going to take 3 plus 4 plus 5 and say this is the max path running through here if we are allowed to split. Now, this isn't the value that I'm going to return to the parent. The reason I computed this value is so I can potentially update the result, right? And we are going to update the result because this is 12. So far, our result is 5. So we can say that our new result now is going to be 12. Now, what's the value I want to return up to my parent? Remember, what this guy wanted to compute was what's the max it could have if it was allowed to split to the left and it was allowed to split to the right. So from here on, we don't want to split twice. So the question I have for this node when we're returning up to our parent is what's the max I could get running through here if we are not allowed to split? So how am I going to get that? Well, I can take this 3 and add it, but then I have to look at my left subtree and my right subtree and take the max of both of these, right? I have to take the max of them. I can't choose both, so I have to choose one of them. I'm going to take the maximum, which is going to be 5. So I'm going to say 3 plus 8. That's going to be the value that we return. So notice how for each node I'm marking what's the return value from that node going to be. So it's going to be 8 in this case. So then when I return back up to the root, I'm going to say, okay, from here, what's the max path we could get? Well, I'm going to take the node itself, 1, take the left, which is 2, and take the right, which is this path, right? Notice how we don't split. It's going to be an 8, which is going to give us 11. Now that's not bigger than our result, right? So we actually don't update the result in this case. And of course, this is the root node, so it's not going to end up returning to its parent. But what if it did have a parent? What would it return? Well, we would take 1 and then add it to the max of the left or the right. Of course, the right is an 8. this is the path. So we'd say 1 plus 8 is going to be 9. 9 is what we would return to our parent. That's the max path we can get from here without splitting. What would that path look like? Well, of course, it would just be this, right? Notice how this is a path. It never splits. So that is the main idea for this problem. There's one last quick thing I want to go over. So the return value, of course, is going to be for every node, what's the max path without splitting, and we are going to still calculate what's the max path with splitting and use that to actually update our result. We're going to keep this as a global variable because it just makes the code easier, but it is possible to solve this problem without using this global variable. And by the way, if you've been noticing, we're only going to be looking at each node once, so that's going to be a time complexity of big O of n. The memory complexity, of course, is going to be the height of the tree, which is usually log n if it's a balanced tree. But one last case, remember this tree could have negative numbers. So for example, let's say this was a -4 and this was a -5. So then from this left subtree, we would return a -4, and from this, we would return a -5. So then, when we're actually computing, okay, what's the max path that could run through here? And let's say we're doing it for the one that we can't split, right? Where we don't split. So we either choose the left or the right. And as I mentioned, how we're doing it is we're just taking the max of the two, right? So in this case, we would take the max of -4 and the max of -5, right? And of course, we'd say the max is -4. So then when we're up here, what we would end up computing is 3 plus -4, which is going to give us -1, right? -1. So what we would say is, okay, the max we could get here without splitting is going to be -1. But that's not actually the case, right? Because to get the maximum path sum from here where we're not allowed to split, it doesn't necessarily mean we have to include the children, right? They're optional. We could actually choose to not include either of these, and that's what we would want to do because they're both negative anyway. Why would we want to include some negative numbers? So when we're actually taking the max of the two, we're actually going to take the max of 3 values. We're going to take the max of the left, right, and potentially 0, because if we just add 0 to it, this will stay the same. So those are the key ideas I wanted to go over. I think that is enough for us to dive into the code to solve this optimally. So like I said, we're going to have a global variable for the result, and initially we're just going to set that to the whatever value happens to be at the root. So the reason I'm making it a list is because that'll make it so that we can modify it within the recursive function a little bit easier. So we're going to have a recursive DFS. We're going to pass in whatever root node we're traversing, and that's really all we have to pass in. So now the base case is that if we don't have a root, like if the node is null, in that case, what we're going to return is just 0. That means we're not going to be adding anything. And so we're going to be returning, I just added a comment, we're going to return from this function the max path sum without splitting. So we want to get the max path sum. So of course we have to do this recursively. So let's get the left max, and we can do that recursively, just pass in root.left. If it's null, of course, that's just going to return 0. We're also going to get the right max, passing in root.right. So the first thing I'm going to do is compute the max path sum with a split from this root node. So basically what I'm going to do is I'm going to take the root.value and add it with the left max and the right max, right? Because we are splitting from this root node. Now, of course, these left and right maxes could be negative. So what I'm actually going to do before that is update them. So we're going to set left max equal to the max of itself and 0. And do the exact same thing with the right max. So it's going to be set to the max of itself plus 0. So here we're going to be computing the max path running through here. So we're going to take the root value, the left max, and the right max, add them together. Now this could potentially be our new result. So let's see if it actually is. So result at position 0 is going to be set to the max of itself, or this value that we just computed. So this is the part where we're actually computing what could actually be the updated result. Now, what the return value, remember, of this function is not going to be the same as this. The return value is going to be what we compute without splitting. So the return value is going to be return root.val plus whatever the max of the left max and right max is, right? Because we can't choose both, because if we choose both, that means that we're splitting. And so that's actually the entire function, right? You can see when we handle the recursive case well and we take the max of it and 0, then we really just have two main computations we're doing, right? The max path sum with a split and the max path sum without a split. Of course, this one is going to be the return value, and after we're done with that, all we do is call our DFS passing in the root, and then that will update our global variable up above, which is the result. Then we can go ahead and return that result, and that is the entire function. I'll run it, and you can see that it does work. Now, you might think it's a little bit cheating to even have a global variable like this, and it's actually possible to solve this problem pretty easily without a global variable too. I just didn't show it. The main way you would do it is, instead of computing this and updating a global variable, what we could do is we could basically return two values from this function. So we would return the max path sum with a split and the max path sum without a split. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Yeah, I still don't understand it really well, but I'll move on to the next one. I think I'm gonna separate less time for each one of them. I think like 20 minutes. I kind of wanna go over trees more to understand it, because I know I don't understand it now, and what I should be doing is probably going to the previous problems. It's the same name. Oh no, I had opened this before. But I want to finish the list fast first, just so I know roughly how the other problems are going to look like and what kind of thinking they involve. So I think I'm going to separate 20 minutes for each instead of 30. And then hopefully I can finish this by next week. Serialize and deserialize binary tree. Serialization is the process of converting data structure or object into a sequence of bits so that it can be stored in a file or memory buffer, or transmitted across a network connection link to be reconstructed later in the same or another computer environment. Design an algorithm to serialize, deserialize a binary tree. There's no restriction on how your serialization, deserialization algorithm should work. You just need to ensure that a binary tree can be serialized to a string, and this string can be deserialized to the original tree structure. Clarification: the input-output format is the same as how LeetCode serializes a binary tree. You do not necessarily need to follow this format. So please be creative and come up with different approaches yourself. Even though I want to go through these problems fast, and I'm probably not going to be able to solve them, I still think it's worth it to, instead of just looking at the solution right away, to force myself to try to think about it, just so I'm more aware of the way that I'm thinking, and how what things are missing in my thought process to solve these problems. Your codec object will be instantiated and called as such. So I have to serialize this stuff. Gonna reach a single string. So can't I take just that? It's obviously not gonna be transforming root into a string. That wouldn't make any sense, I think. Because then how are you gonna deserialize? I wonder if you can parse the string into the original stuff. But this probably doesn't work as well, because it's a nested object.
Feel the sky, feel the soul of sea. Feel the smell of burning me. Feel the fly, feel the world of me. Feel how your soul inspires me.
I guess I don't understand exactly what I have to do, because no, yeah. If I put the each node, but then I have to capture all the information of the left and right. That's the problem.
Feel the sky, feel the soul of sea. Feel the smell of burning me. Feel the fly, feel the world of me. Feel how your soul inspires me.
Maybe you could do something. You could just try this stuff. The problem is that I'm not even sure if I understand. What they're trying to make me think here, because I imagine there's a bunch of different ways to transform each root into a string, and I don't know how to break it down. Like what points can I create multiple different strings and then concatenate them at the ends? and what points I'm gonna break it down, each one. Like, is it better to create one string for each node and then put them on a list or something like that? Or should I be trying to put all of the nodes into one string each time? And left plus the problem is the value then, because I can't call with the value. Can I print this to see what I get? Oh, I forgot to do this. I wonder if it's gonna let me concatenate as well.
I know the story of your life through winter storms and summer skies. There was a time when you were young and free.
And if I do string, I think that doesn't make any sense as well. The other issue that I need to figure out how to search for is this thing here. I don't understand why in some cases I get none type. Because if in my mind, if the left node from this one is none, it shouldn't pass the if statement. And sometimes it works, sometimes it doesn't. I don't understand really how what's going on. Maybe if I print blah, blah. It's probably because it's an object, but doing this also, I don't think it makes sense. Yeah. Oh yeah, and I'm passing as a string to the function, which also doesn't work. I should be passing like this, but this way I also don't think it's gonna work. Yeah. Again, forgetting to do this stuff.
You're my river running high, run deep, run wide. I follow you deep sea, baby. I follow you, I follow you, dog doom honey. I follow you, I follow you deep sea, baby. I follow you, I follow you, dog doom honey. I follow you,
I'm getting done here. Doesn't make any sense. That's because I'm not returning it. That's why I'm getting down there. I think. Yeah, I have no idea how I should do this. Not even how I should think about it. Oops.
Hey everyone, welcome back, and let's write some.
We'll be right back. Alright, I'm back. Let's put the camera. I think what I'm gonna do is yeah, maybe. And the thing is, these ones have few problems. So maybe I'll do this 6 more, and then when I get your graphs, I'm gonna stop. And I think I'm gonna do the rest of them off stream. Not off stream. I'm gonna record myself doing them, and I'm gonna stop every now and then to read the book. I think that's gonna be better. And once I'm done with the list, then I'll go back and I'll study in-depth trees and probably graphs as well. I'm gonna have to do it because I suck at it. Also linked lists probably.
More LeetCode today. So today let's
Oh, and
solve-
after I'm done with these problems, I'm gonna finish reading the Ethereum article, and then I'm probably gonna be done for today.
serialize and deserialize a binary tree. Basically, what we're trying to do is we're given a binary tree, right? And we want to write two functions for it, serializing it and then deserializing it. When we serialize, we're taking an object, right? And this object in memory, it could be anything, right? Like you don't know where this node could be in memory. You don't know where this node could be. We know that there's some links and stuff connecting them all together. But what we want to do is take this and put it into a very easy to read string that could be passed around easily, right? So basically, for example, we could
Oh, forgot to change that volume.
we could convert this entire tree into a string, something like this, right? 1 is the root node, then there's a 2, then there's a 3, then there's a couple nulls because 2 doesn't have any children, and then there's the other nodes, 4 and 5, right? Basically, this is something that's easy to use and pass around, right? And we also want to be able to take a string like this and then turn it back into a tree. So we have to keep that in mind. It's something that could be, taken back and forth, easily reversed. So there's a lot of different ways to solve this problem. I'm going to show you a pretty easy and straightforward way to do it. You could use breadth first search, basically taking the tree and then serializing it level by level, and then, reading through the input level by level, etc. But there's also a way to do it with depth first search using pre-order traversal, and I'll show you this way because it requires a little bit less code. So like I mentioned, we're going to be doing this with pre-order traversal. So let's just see, what would a tree like this, if we converted it into pre-order traversal into the form of a string, what would it look like? Well, obviously the first value is 1. So we're going to say, okay, the root node is 1, right? That's what pre-order means. We're going to do the first node. Then we're going to recursively do the left subtree with
I think one of the reasons why this might be harder than the previous problems is that the previous ones, I'm a lot more used to doing things with them as I'm programming to build stuff. And the other ones I haven't seen them that often, except for when I build stuff with the network X, but I just use the library and I didn't have to think about the graph necessarily. Or maybe I thought about it, but I wasn't thinking in terms of graphs or trees. I was just thinking about how to solve from thinking about the objects themselves. So that might be the reason why these ones are harder than the other ones. I just haven't seen them that often.
Pre-order traversal, and then similarly after that we're going to do the right subtree in pre-order traversal. Now obviously we want to be able to separate values, so we're going to use a comma as a delimiter, but you could use a space if you really wanted to, or use something else, but I'll just use a comma. So now let's recursively do the same thing for the left subtree. So obviously we have a 2. Let's add that 2 because we're doing pre-order. And now let's do the left and right subtree of 2. So first let's go to the left subtree. Now we're going to see null, right? This is null. It's empty. There's nothing there. But we are going to add that to our string just to indicate to us that this left portion of the subtree cannot be continued, right? And you could add the word null, but I'm just going to use a capital letter N to indicate that. So that's going to be our special value that indicates an empty node or empty tree. Since we finished the entire left subtree and we know that it was a null, right? So that's basically our base case. That tells us we can't go any farther here. So now what's our right subtree for 2? It's also null. So we're going to add another null. And see how we've done the entire left subtree here? So now we can start going down the right subtree. So of course the first value is a 3, so let's go ahead and add that. And similarly, we're going to do pre-order traversal on the left subtree. Now you can basically see this is the exact same thing that we did up here, right? 2 was a node and 2 had no children, so left and right child of 2 were null. That's the same that's true for this 4 node. So we're going to add 4, and then we're going to add the 2 null nodes, basically indicating that 4 does not have any children. N. So now let's go do the right subtree. Basically, you can probably tell what I'm going to do here. So I'm running out of space, so let's put the 5 down here, comma, and then a couple empty null nodes. And now we're done.
Another thing that is a little bit different than doing this, different from doing this and the stuff that I was doing in the past, is that the stuff that I was doing in the past, I can search everything. I search a lot more often. So that might be the reason why, because you don't feel like you get stuck as much because you can just search instead of having to think about it yourself or how to solve the problem. So it's a little bit, it's a different kind of challenge, I think. And building stuff is more about understanding, or I think it's also more aligned with the way that I am. because it's thinking more about the big picture and figuring out how to connect each thing. And this stuff was more like a mathematics, or it's something that you have to think about more, like. But it's kind of it seems like it's a little bit different, the way that you should approach each one. But obviously they are integrated because it's just a distribution.
Right, that was the entire string. So now I'm going to get rid of this tree, and we're going to see, is it even possible for us to be able to take a string like this and know exactly which one is going to be the left node and which is going to be the right, etc., right? Well, we're obviously going to use pre-order traversal on this string, basically, to create a new tree. And I'm going to show you that it is possible, that this string is actually not ambiguous, because clearly you can see, okay, 1 is going to be the root node, then the next value must be the left. If this were a null, that would mean that 1 has no left subtree, right? So we could just put null for its left subtree. But clearly this is not null, so that means 2 is the left child of 1. Next we see, okay, let's create the subtree for 2, right? Well, its left child is null, and next its right child is also null. So therefore, 2 is not going to have anything, right? So that's basically the idea. So now let's actually do it. Okay, since we know we created the string with pre-order traversal, that's basically the idea we're going to use. So we're going to have a pointer, we'll call it I, that's going to basically tell us what index of this string that we're at. Well, in reality, what we're
And
going to do...
another thing that I'm realizing as well, that I can sense, I think I'm kind of getting the same feeling that I got when I started out with the free code camp challenges, where it's demotivating because you can't really tell how practical this is gonna be, when, like, I know it's gonna help me and improve me as a programmer, but it's difficult to see the result right away. And it was the same thing when I started, that I remember I was doing the free code camp challenges, and you're kind of like, it's a part of you don't want to waste energy thinking about, like, really trying to solve it, because you can't really see the point of doing that. I tried to do the LeetCode contest yesterday, I think, and I just didn't feel like it felt like a waste of time to just spend energy trying to think about something that is completely irrelevant. But it's just the initial barrier, I think, because your brain can see the connection between these things and your actual skills. So I guess that stuff just comes with time, because now, the last time that I went back to free code camp, I just saw the challenges completely differently. So I think after I'm done with this study, and then I go back, and then I go back again to LeetCode, I think it's gonna improve a lot more my willingness and to do these challenges, or my thinking patterns.
We're actually going to take this string and then split it based on the delimiter comma. So then it's actually going to be an array, but I'm not going to redraw that just because it's pretty straightforward what we're going to be doing with this string. So first one is non-null, so it's a 1, right? So we are going to create a root node with the value 1. Now let's create the left subtree, similar to pre-order traversal, right? We're creating the node now, then we're going to do the left subtree, then we're going to do the right subtree. The question you might have is, how do we know when the left subtree stops and when the right subtree starts? I'm going to show you it's actually simpler than you might think. So we know that the first value here is going to be the left child. If this were null, we would put a null here, but it's not null, it's 2, so we are creating a 2 node over here. And once again, recursively creating this subtree. So start with the left. So this first value is going to be the left subtree. It's a null, right? So since it's a null, that means we can't continue this subtree anymore, right? So that means whatever value, so we're done with this first null. Now, whatever value comes next here is going to be the value in the right subtree of...
And the reason why I'm saying this stuff is because I'm recording this stuff to show my progress. And I think that's something that I realized very often in everything that I've done in the past as well. I think that's the reason, that's the difference between people that get good at stuff and people that don't, is that this initial barrier, or if it feels like you don't know, or it gets demotivating, and because you can't associate, you can't see the results right away. I think that's what separates people that actually become really good, because you have to train yourself to become used to being in this state and pushing through. And I think that's the difference. So the more that I do this kinds of things, the easier it becomes for me to associate this feeling of not knowing how to do something and pushing through and then seeing the growth and then realizing that if you keep going every day and you just keep pushing, like the feeling is never going to stop because you're always going to be at the boundary of what you're capable of. But when you look back at it, you grow a lot, and it's the small steps that make the difference, I think. Like the everyday not forcing yourself, but having the discipline to try to do this stuff, even though you suck at it. I think that's the main point of doing this.
This 2 node, it happens to also be null, but maybe if it wasn't a null, maybe it could have been a 3, right? That's when we would put 3 over here, but clearly it's not, it's a null, so that means we can actually stop this subtree as well. So since both of the children were null, that means we're actually done creating this entire subtree. We reached our base case, basically. So we're done with this. Now the next value that comes in our string is clearly going to be the right child of 1. So the 3 is going to be the right child here. And now, of course, pre-order traversal, we're going to fill in the left subtree of 3. So what's the next value in our string? It's a 4. So this does have a left subtree. 4. Continuously, we're going to be doing the left subtree of 4. We see it's a null. That's our base case. So we're done with the left subtree of 4. Next, we're looking for the right subtree of 4. So what's the next value in our string? It's again null. So we reach the base case. We can be done with this entire subtree. So we're going to pop back up recursively over here to 3. And now we know we need to fill in the right subtree. It could be null or it could be a real value. Let's find out. Well, the next value in our string is a 5. So therefore, this is going to be 5. So next we see that, okay, left child of 5 is going to be null and right child of 5 is going to be null, right? So clearly what you can see here is that for every single leaf node we have in our tree, we specified what their children were going to be. We specified the leaf node 2 has 2 null children, leaf node 4 has 2 nulls, and leaf node 5 has 2 nulls. That's how you know we're done with the entire string. We're going to stop here. We know that there's nothing left to do, right? Every single leaf had null children. Therefore, we can't possibly continue this tree, right? So we're done. So that's why it's not ambiguous. And by the way, what do you think the time complexity of this was? Well, we know that pre-order traversal is pretty linear, right? So basically O of n for serializing and for deserializing. This problem is actually a little simpler than you might think, for a hard problem at least. So now with that being said, let's jump into the code. So good thing for us, we only have to fill in 2 functions. So let's start out with the serialize. So we're going to be given a root node for a tree and we want to convert it into a string and then return that string. So let's start with a empty string initially, right? And actually just to make things a little bit easier, I'm going to set our result to an array. I'm basically going to be adding strings together. Like for example, if we had a node 1, I'm going to add it like this. If we had a node 2, I'm going to add it like this. And then at the end, I'm basically going to be joining all the strings together with a comma delimiter. So I'm going to define a function inside a function just because it's easier once again, right? So this is going to be our pre-order depth first search. We are going to be passing in the current root or the current node that we're visiting. And of course, we know that the base case is if the node is null. And in that case, what are we going to do? Our special character that we're going to define is going to basically be a n character. So to result, I'm going to append an n character, and then we're going to return. If it's not null, then we know we can append. Since we're doing pre-order, we're going to be appending before we recursively do depth first search. We're going to append node.val, but we know it's going to be an integer, so we're going to convert it into a string. So node.val converted into a string, appended to result. After that, of course, we just call our recursive depth first search on the left and right subtree. So depth first search on node.left and depth first search on node.right. And we don't even have to call our return function because once this is done executing, it's going to basically return by default. So once that is done, we know that our result is going to contain all the strings that we want it to. So basically what I'm going to do is return the result joined by a comma delimiter. So comma dot join everything in result. Oh, but I almost forgot we actually have to remember to call our depth first search function. So I'm going to call it passing in the root value. So our serialize function is actually just as simple as that. So next we're going to be moving on to our deserialize function. So we're going to be given the data, right? We know that the data...
So this is the thing that I didn't understand. Is if I'm supposed to... What exactly I'm supposed to join into the string, because if I'm only joining the value, I'm missing the structure. But I guess not.
Is going to be comma delimited. So we're basically going to split it based on that comma into an array, a list of the data that we're going to be needing. So I'm just going to call that vals. And I'm also going to create a pointer. I'm going to call it self.i, self, because it's going to be a member variable of this class, basically because we want it to be global, because I'm about to define another recursive function inside of this function, and I don't even need to pass any variables into it because the self.i is global. So I'm going to initialize this to 0, indicating we're going to start at the first value in our list of values. And so once again, we're going to start with the base case.
Maybe it's because the way that you append preserves the structure, because of the recursive calls.
Now, what's the base case going to be? Well, if our pointer is pointing at a value in the vals, and if that value happens to be null, now how do we know if it's null? Well, that's pretty easy, right? We can say vals at index self.i, and if it happens to be equal to the character n, we know that's null. So what are we going to do? We're just going to return the base case. We're going to return a null node. If it's not null, that means we have some work to do, right? We have to create a tree node with that particular value. But we know this vals at self.i, we know this is going to be a string, right? So, and we know that tree nodes have integer values, so we're going to convert this into an integer before we pass it in. And so this node is going to be referred to as node. One thing I actually almost forgot. If we're saying that the value at this vals is null, so we're basically saying we're done visiting this, right? We're returning null for this n in our values array. So before we return, we want to make sure that we increment I. So self.i plus 1, so that next time we call a function that we're at the appropriate value in our list of values. And that's exactly what we're going to be doing down here too, right? So since we're already using the value at self.i, once we create this tree node, we know we have to increment our pointer I so that we can be moving on to the next value that we need to create a node for. So I'm going to call depth first search. Remember, we don't actually have to pass any parameters into this, and the return value for this is going to be the subtree I created for node.left. It could be null or it could be something else. Now, after calling this depth first search function, we don't have to increment self.i because that's going to be happening recursively. So once this is done, we're going to do the exact same thing for the right subtree. So node.right is also going to be basically whatever depth first search returns for us. And once all of that is done, we know that we can simply return the root node that we ended up creating. And then once that's done, we've basically defined our depth first search function. So what are we going to do? We're just going to call that depth first search function and return the result, because for this function, we're taking in a string of data and then converting it into a tree and then returning that tree. This problem is not too bad if you do have a pretty good understanding of depth first search or pre-order traversal, or, just general binary tree traversals. You could do this with breadth first search if you really wanted to. It just takes a little bit more code, but you can see that this is a pretty efficient enough solution. This is about as good as it gets. So I hope that this was helpful. If it was, please like and subscribe. It supports
So it
the channel
seems like the
a lot,
main
and I'll hopefully
takeaway
see you pretty
from
soon. Thanks for watching.
these problems here, from the tree problems, is understand really well that first search. The other one that I forgot the name, which is the horizontal one, like breadth first search. So I think these two ones that I need to study the most, and also recursion, because recursion is really difficult for me. And maybe we should show everyone actually to understand how it works. And I think all the three problems are probably gonna be those three key principles there. So it's usually gonna be, from the list that I've seen here, is gonna be some sort of traversal like that, either horizontal or vertical, and then a flow of if-else statements to determine what kind of logic you wanna get from the tree. It seems like everything comes down to that. A tree pronounced as trie or prefix tree is a tree data structure used to efficiently store and retrieve keys and data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. Implement the tree class. Tree initializes the tree object. Void insert string words, inserts the string words into the tree. So this one, I think. Boolean search string word returns true if the string word is in the tree. Inserted before, and false otherwise. It starts with returns true if there is a previously inserted string word that has the prefix, and false otherwise. Oh, so here should be self to the left. Oh. Am I supposed, because there are no arguments here. So should it have left or right? And the hard thing about this is that I don't really understand what they mean, because the way that I'm thinking about, I can just do a list and then append into the list the word, but that's probably not what they want me to do, because it's supposed to be a tree, but then they don't put left or right here in the init. So maybe I should just try to do that. But it's probably not this. Because, yeah, it wouldn't be the same structure. Yeah, thanks for the follow. I think I'm gonna probably remove that, to be honest. Because I thought about this before, and yeah, not really doing this to gain followers, not right now. So I guess I just did it because it seems like it's a normal thing to do, but the more that I think about it, it doesn't make too much sense, sorry. Maybe in the future, but now I feel like it's not that much about that. It's more about showing me struggling with this, so later on I have this catalog or series of videos of my growth. The other thing that I'm gonna do after I finish this list is allow myself to search more. I think I'm gonna remove this time limit, and I'm gonna allow myself to search in the same way that I do when trying to build stuff and watch videos and stuff like that, and take notes about the stuff that I'm struggling with. And this, I'm not sure why I can't do wording words and soft.words. I think prefix is the beginning of a sentence or a word. Yeah, so I can just look through the thing. Yeah, but it's definitely not what they want. Is it only me, or they don't explain enough about that tree? Yeah, I don't understand also. But maybe it's a problem for people that already know that. That's the thing. I've heard about tree, and from what I remember, is something used to connect words. It's like they tell here, like a tree, but I'm not really sure. Like I don't know the implementation of that in Python, and I'm not sure what's the relationship there, because obviously it's not a tree if it's a different name, so there must be some difference. How a tree would look like. Yeah. Is it a binary tree? I have no idea. It's fine though. Because you can also just look it up, right? As you're doing this. It's like, the thing is, right now I'm doing this to purposely fail, let's say. Like I don't expect I'm gonna, obviously I wanna solve it, but I expect I won't be able to solve any of these problems here. It's more about going through this struggle of trying to think about how I can get to the solution. So later on, once I understand more, I can make the connection of, I can remember the way that I thought the first time that I saw the problem and the way that I thought before, and then I can start to upgrade the way that I think about these problems, because ultimately the goal is to be able to improve the way that you approach the problems themselves. So and I think that's a good way to understand, look at a problem, improve it, being able to look at a problem and understand what kind of thinking patterns you need to apply on that problem. BFS search. Could be, yeah. I just don't understand how I'm supposed to insert here. That's the thing. Because if each word, if I'm supposed to have a list at the creation of the thing and then append each word, then I think it's different. But as far as I know right now, the tree structure is supposed to have a left and right value. And every time you initialize one, you need to specify the right and left. So maybe that's what they want me to do, but I'm not really sure. Like left equals none. And then there's also the value, but the thing is, the way that I was doing before passes the example task, so maybe I was in the right track. Let me go back and see what the mistake was. So it starts with dog. Oh, it's because I'm looking to see if it exists on the word, and not if it starts with the word. That might be the problem. And so maybe this is something that I can search. It's not related to the... But let me think about it first. Maybe we can split based on the length. Or I have to do inside the loop. I don't think you can splice strings. I don't think you can do this. Oh, so I can't do this. Four, five. So it again starts with. I should print prefix as well. Oh, I'm getting the end. So maybe if I do this. And it probably has to be -1. God damn. Output limits. Oh, there we go. Nice. Wasn't expecting to get that. I probably suspect it isn't the best approach.
More neat code today. So today let's solve implement try, aka a prefix tree. So a try or a prefix tree is a special type of tree, and it's used to efficiently store strings. And the applications are some stuff like autocomplete and spell checker. The reason is because the prefix tree allows you to efficiently filter and search based on prefixes. So let's look at the actual implementation of it. So we're going to have a object. That's what we're going to be doing this time, a try object. And our job is to fill in 3 functions. The first function is going to be inserting a word into the try. The second function is going to be searching for a word in the try to see if the word exists. And the third function is going to be to check if there is a word that starts with a given prefix. So those are the 3 functions we're going to do. And let me just go through the rest of this explanation, and then I'll show you what a try actually is. So here you can see basically what we're going to actually be doing. They're going to be instantiating the try, right? We're going to be inserting a word such as apple, right? Then we're going to run search. Does the word apple exist? Well, we just added it. So of course we're going to return true. Apple exists. Then we're going to check, does the word app exist? It does not. The word app does not exist. And third, we're going to try starts with app. Are there any words that start with app? And answer is yes, so we return true. Remember, apple starts with app, so we return true. The prefix, right? This is the prefix. App is the prefix of apple. So now let me show you the actual data structure. So let me show you what a try is. And in this problem, they told us that the limitation is that the words are...
One thing that I've been thinking about is the relationship between these data structures and graphs, because trees use recursion. So some graphs probably use recursion as well. So I wonder if there is a way to kind of capture, or maybe it is graphs. Maybe fractals are graph data structures. So that's a question I have in my mind. Might be an interesting idea to improve both on the graphs, trees, and also to advance on the stuff that I was curious about. Just try to do something that transforms a fractal into a data structure or something like that.
We're going to only have characters from lowercase a to z, right? So this is lowercase a to z, so that means we're going to have exactly 26 characters to worry about, right? But so this is a tree, right? It's a prefix tree. It's a special kind of tree. So initially our tree is going to be empty, right? But let's say we want to insert apple. So if we want to insert the word apple, how can we do that? Well, this is what we're going to do. We're going to create a node for the lowercase letter a, right? Then we're going to create another node for the lowercase letter p. And we're going to basically keep doing this for every character in the word that we're inserting, right? We're going to say...
And another question I have that I need to remember is, what happens if the size of the tree is bigger than the size of the stack? Can you do that first search if that's the case? Because isn't the tree always going to provoke our stack overflow? So how should deal with that? And then I was thinking about, maybe it's possible to divide the tree. So when you get to a node, a certain node, you make that node equal to the root. Again, so you kind of like split the tree. And it might be an interesting idea to see if there's something about that, because I suspect there's probably an algorithm that does that, or just splits trees. But then I'm not sure how it would work, because it would have to separate the tree into different functions that run at different times. Yeah. So that's another thing to think about it.
A, insert it, P, insert it, second P, keep doing that. And every time we're inserting a new character, we're going to add it as a child of the previous character. So we inserted the word apple, right? We can clearly see that. One more thing we have to do to say that this is the word that we inserted is we have to mark the end of the word, right? So this is the end of the word, right? The letter E is the end of the word. So we're going to mark it such that so that this is identified as the end of the word, right? Not, for example, this, right? If we mark this as the end of the word, then we're basically saying we inserted the word AP. But we know we actually did apple, right? Full on apple. This is the last character. So we mark here as the last character. We are marking it, even though it's kind of self-explanatory because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe. So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So potentially we could have a node at the first layer for every character, right? So A, B, C, D, etc., right? We can have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with a D. So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder node, right? It doesn't have any characters, but it's considered the root, right?
Yeah.
And so we're going to...
So what I did wrong is obviously I didn't know how to do it. This is a hacky way to solve this, not the correct solution. But I put one word, the entire word instead, on each one, and I should split by characters, and then maybe he's gonna create an object to find the position of them.
Check, does this root have the child of the first character that we're looking for, right? So take a look, this is the word we're looking for. Obviously, we're looking for the character A. So we check, hey, there's the A, lowercase a, right? It's the first character of the word. That's what we're looking for. Great. Now, for this A, we're looking for the next character, right? So does this A have a child P character? It has exactly that. So we do have this P, right? And this is what we're doing, right? We're going character by character in the word we're searching for and checking if a node exists for each character consecutively, right, as a child. So next character P, does this have a child P? Yes, it does. Next character L, we have a child L. Next character, E, this is the last character, so we do have an E over here, right? And last thing that we have to confirm is, okay, this is the last character. Is it marked such that this is the end of the word? Is it marked as if it was the end of the word? It's blue, right? That's what we're doing to indicate that it's the end of the word. So it is, right? So clearly we do have apple. We search for apple. What do? We return true because apple does exist in the try. So next, let's run search again. And this time, let's check if a word app exists inside of our try. App, right? Not apple. So obviously we know that starting from the root again, we do have a lowercase a, just like we checked. We do have a lowercase p after that, and we do have a second lowercase p. So since we do have all three of these characters, right, a, p, p, shouldn't this function return true? No, we're not returning true. And the reason is this node is the last character of the word, right, p, and it's not marked blue, meaning it's not marked as a word, right? Remember, we only inserted apple into our try, right, into our tree, and we marked this as the end of the word. We never inserted app into the tree, so this is not marked as the end of the word. So we return false for saying that app does not exist in our tree. App is not a word yet. Next, let's run another function on our tree or try. We're going to check, does a word start with app? How can we check if a word starts with app? Well, we're basically running the exact same thing we've done, right? We're starting at the root. We're going to check character by character. So this is pretty, like all three of these functions are pretty similar, right? We're checking character by character for all of them. Start at A exists, check P exists, check another P does exist. So since we found all of the characters, right, we're basically guaranteed that either this is a word itself, which clearly it's not, right? We never inserted app, or we're guaranteed that there is some word below that has been marked, right? Because if we inserted these characters, we only did that because we were inserting a word, so there's guaranteed to be at least something that is marked blue down here, right? So once we found this character, the second P, which is all the characters in here, then we can say true, right? There definitely exists a word that starts with app, right? And so this starts with function is the main reason we're even implementing a try in the first place. Because if we want to insert words and search for words exists, right, to check if a word exists, we could just use a hash map for that, right? Because hash maps can, or hash sets can do both of those things in O of one time, right? But this is really the problem. Starts with, it allows us to check prefixes, right? So now let's say we were inserting another word. Let's say we're inserting the word ape, right? A-P-E. How are we going to do that, right? We're inserting another word. What does that mean? Are we going to say A-P-E E and then just create a separate node for each of these as children, right? And just connect them such as that, right? This is a child of A, this is the child of P. Are we going to do that? No, because we could reuse it, right? Why would we have duplicate A's in the first position when we already have an A over here? So if we are inserting this word ape, we're going to leverage this A that we already created. Great. And then we're adding the second character, P. We're going to leverage this P that we already created. And so we've inserted the first two characters. What about the last character, the E? Do we have an E over here? No, right? There's no E in the third position. So what are we going to do? We're going to create another child node, right? Now we create an E. And last but not least, we mark that this is the end of a word. So you can see that a try actually has the potential to be pretty efficient because we are reusing a lot of nodes, right? We're not necessarily creating a separate node.
I think I understand now what I was getting wrong. Is because the difference between the try and the tree is that the tree has the lists based on value, right and left, and the tree is based on the word. So that's why they didn't put it. Yeah. It's a lot harder if you do it like this, obviously. But I still don't understand really well. I think I kind of get it, but like, what's the practical application of this? I think the purpose is that it makes more efficient because you're reusing the same characters. But I don't understand why would you do that? Would you put this in this format? I think I'm gonna bring it back.
For every single word. Now, let me just show you one last thing before we jump into the code. So we're going to do one last function. We want to check, does any word start with B? And I'm just illustrating why we're even implementing a try in the first place. It's because the starts with function is very efficient compared to other data structures. So for example, let's say we had a list of words, a list of strings, and let's say the size of that list was equal to 1,000,000, right? How long would it take for us to check if any word starts with B? Worst case, we would have to check every single word in the list and check if it starts with B. And what if there was 0 words that started with B? Then every time we would have to go through that entire list of 1,000,000 words. But with a try, like we've implemented right now, it's very efficient. Here you can see we have 2 words, right? We have 1 word here and we have a second word here. And it's possible we could have 1,000,000 other words, right? Like clearly there's probably a lot of words that start with the character A and maybe so on. But
I wonder if you can use this to teach yourself a language. Yeah, exactly. Very interesting. Because it's kind of like an efficient dictionary if you think about it. So I wonder if you can put all the words of a language into a try, and then maybe make an association with other languages. It sounds like an interesting. Maybe someone has done this before, but maybe it's useless. I don't know.
When we run this function starts with B, all we're checking is we're starting at the root. We're checking, do we have any children with the character B, right? We check this first layer. How large is that first layer going to be? Well, we know that there's 26 lowercase letters, right? So worst case, it would be lowercase 26. And that's pretty efficient, right? So when we check, hey, there's a lowercase a, but there's no lowercase b. So for this starts with function, we can return false. And that was done very efficiently, right? 26 is basically big O of 1. So this is a super efficient way to check prefixes, right? And that's why they call this a prefix tree. Prefixes can be checked very efficiently. So now let's actually jump into the code. All three of the functions, insert, search, and starts with, are pretty similar functions. So even though we're going to write a lot of code, it's going to be mostly similar. So let's jump into that. So our job is to implement a try, but we can't really do that without implementing a try node. So the first thing I'm going to do is create a try node. And all we're going to do is just create the constructor. So in Python, that's what I'm doing. And net is basically the constructor. And I'm just going to have a couple of member variables for this. So we are going to have children of a try node, right? It could have children. It could have 26 children, but instead of doing an array, I'm just going to do a hash map because that's easier. And remember, we can also mark every single node as if it was the end of a word. I'm going to say end of word is going to be a variable. Initially, it's going to be false, but we could set it to true if the character was the end of a word. Notice how we're not actually storing the character itself in the try node. That's going to be implicit from the hash map, from this hash map. So if we were adding let's say a character A, a lowercase character A, we would say to children, we would say children for character A is the key, and we're going to create a new try node for that character A, right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire try node class. Now let's actually get into the try class. So the first thing we're going to do is initialize this. So let's get rid of this comment. And for initializing this, all we're really going to need is a root node, and we can get the rest of the nodes from that root. So we're going to create a root try node, and that's it. That's all we're going to do for the constructor. And once the try node is created, we basically have an empty tree. Even though we have a root, it's empty because it does not have any children. So we technically have not inserted any words yet. But now let's implement the insert word method. For this method, we are going to have to iterate through every single character in the word. So we're going to initialize ourselves. Current is going to be set to the root. So we're going to initially start at the root, right? And then we're going to go character by character in the word. And for every single character, we're just going to check two things. Does this character already exist? If it doesn't already exist, so if this character is not in the current nodes dot children hash map, right? So if this character is not in our hash map yet, that means it hasn't been inserted yet. So what are we going to do? We're going to create a try node for this character. So cur dot children, and the key value we're going to use is the character, and then we're going to create a new try node. So this is how we are going to be inserting characters. To children, we're going to use the character as a key value, and then we're going to create a empty try node. And we're only doing that if the character doesn't already exist. If it does already exist, then we can skip that step and just say that current is going to be set to that child, right? So if that character already existed, then we can just update cur and move to that character and then continue our for loop, right? So we're going to do this for every character in the word. And then by the end of this loop, whether we have to create every node or the nodes already exist for us for this word, right? Let's say it was apple or something. The characters already exist, or we just created them. Now, current is set to the last character of the word. So what are we going to do to current? Well, we're going to mark it as the end of a word. So we're going to set end of word equal to true now, and then we don't really have to return anything.
So that was pretty simple, right? Not a lot of complex code. We did have to go through every character, and we either created nodes or just iterated through those nodes. And the remaining two functions, search and starts with, are actually going to be very similar to this insert function. So now let's get started on search. So we want to search to determine if a word exists or not. So just like the previous function, we're going to start at the root node, so self.root, and we're going to go character by character in the word, and we're going to check if this character exists in our tree. If it does not, so if C not in current.children, if this character does not exist, then what do we have to do? We return false, meaning the word just simply does not exist. If it does, then we can move ourselves to that child node. So we can update cur and set it to the child node of that character. And then we're going to basically keep doing this for every character in the word. If the word doesn't exist, we'll return false. If the word does exist, that means the entire loop will execute, and then then cur will be the last character of the word, and we know that it is a word if cur has the end of word variable set to true. So this is the variable we're going to be returning. If this is set to true, that means this is a word and will return true. If it's set to false, that means it's not a word and our function is ultimately going to return false. And now, last but not least, let's get started with the starts with function. And this function is actually going to be the exact same as the search function, except we're not going to have to determine if it's the end of a word or not, right? We're not checking if it is a word, we are just given a prefix, and we just want to know if there's any word that starts with this prefix. So once again, for the third time, we're going to be starting at the root, and we're going to go character by character in the prefix this time, right? We're not given a word this time. And if this character is not in our tree, so if it's not in the children right now, then we will return false, meaning the prefix does not exist. Therefore, no words start with this prefix. Otherwise, we will shift our current pointer to that child pointer of this character and continue on. And at the end, if we do reach cur, then we can immediately return true because we know that there's at least one word that starts with this prefix. We don't have to determine that the prefix itself is a word. So that is the entire code. I can zoom out so you can see the entire thing. And we just have one small typo over here. This is children. And so other than that, this is the entire code. So today you just learned a brand new data structure, and I hope that this was helpful for you. So this data structure can be pretty useful. It's a rare data structure to see on LeetCode problems, but I hope that you did learn something new today. And if this was helpful, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Yeah. Probably it's gonna be hard to do the other ones. Definitely. I think I understood the high level view of it, but not the specifics there. So to do the other ones in this way is gonna be hard. Design, add, and search words data structure. Design a data structure that supports adding new words and finding if a string matches any previously added string. Implement the word dictionary class. Let me read that again. So supports adding new words and finding if a string matches any previously added string. So very similar to the previous one. Implement the word dictionary class, where dictionary initializes the object. Void add word adds word to the data structure. It can be matched later. Bool search word returns true if there is any string in the data structure that matches word, or false otherwise. Word may contain dots, where dots can be matched with any letter. Yeah, so I'm not sure. Let me see if I can remember class tree node or tree try node. Solve. Do I put no? I don't put solve here. It's self.children because this self.end words is false. And self.roots because tree node. I think as far as I remember it was something like this. Then on this one, need to map. And then create the word in the hash. But this is the part that I don't remember really well. What I'm supposed to do. I guess each one is gonna be a tree node. So maybe I need to do self. Children C equals tree node. And then I don't remember. I don't remember how he handled when the characters are the same. Or maybe he did if C in children. Yeah, I think that's what I'm missing. But I don't think he wrote it this way. I'm probably forgetting something. Yeah, how do I connect the words? Because if it already exists in the dictionary, it needs to branch off into another one. I don't remember how to do that. If it doesn't exist, then it becomes a value, which is a tree node itself. So maybe it can't be a nested one. Or maybe I should look into it, the solution again. And try to... I don't really see the difference between this one and the other one. It feels like they are pretty much the same thing. But this one has less methods than the other one. Let me go back and watch the video again. Yeah, exactly. And then search is the same as the search prone the previous one. But I don't remember, I can't remember how he did to add the letter once it already exists. Because I remember he said you have to branch off because if you have apple and then you want to insert ape, you already have the two first letters, so we branch off. But I don't remember how he did that. It's probably a new else statement. I think I'm gonna have to watch the video again.
Hey everyone,
Obviously, I'm gonna jump to the code parts.
value we're going to use is the character, and then we're going to create a
Oh, he created the root first. Also forgot about that. That's why I felt like this was off, but I couldn't. So is it equal to self.children? No, self.root. Yeah. Because it's on this class, not the other one. Oh, now I think I understand. Because I'm confusing this class with this one. This one is the parent one that has the nodes. So I need to add the letter to this one. Probably. Children. Because it's a tree node. Where dictionary contains, which is the tree nodes. So I'm checking if the character exists in this object, which is the children of this root here. And if it isn't, then I create, which is another object. I think this is correct.
new try node.
Current children. That's what I forgot. Yeah, because I don't want to append to the root. I want to append to the object of the root. Yeah, because cur is the tree node object, not the. So it doesn't make sense to do it the other way.
So this is how we are going to be inserting characters. To children, we're going to use the character
But this part I forgot now. The other statement to add.
as a key value, and then we're going to create a empty try node. And we're only doing that if the character doesn't already exist. If it does already exist, then we can skip that step and just say that current is going to be set to that child, right? So if that character already existed, then we can just update cur and move to that character.
Yeah, this one I'm not sure if I understand. Maybe that's the point. Maybe that's why the other one is different, but because why are you making the root equal to the current character? Oh, you're making equal to the children. Yeah, but it doesn't make sense. Wikipedia. No, but I guess I think I understand the visualization. I just don't understand is the connection that I'm making some mistake. Let me think about this. Well, I didn't write it down. So cur becomes cur children C. So let's say it doesn't exist. You're gonna create it on this object, which is a child of this one. Right? So now let's say that C exists here, and itself is a tree node. So next time you're accessing this, you're saying that the parent is gonna be equal to this. That's why it doesn't make sense. Goes level by level, letter by letter. So it's like a pointer. And it's hard for me to think about it this way. Because to me, it's more like the object, the parent. Just like in the tree, you have the root node. Oh, I guess is making another root. Because it already exists on the... The thing that is trippy is that it's making a root inside of this self. Because it feels like it creates the top node first, and then if the letter already exists, it creates another top here, but it's inside of itself. It doesn't make sense to me.
And then continue our for loop, right? So we're going to do this for every character in the word. And then by the end of this loop, whether we have to create every node or the nodes already exist for us for this word, right? Let's say it was apple or something. The characters already exist, or we just created them. Now, current is set to the last character of the word. So what are we going to do to current? Well, we're going to mark it as the end of a word. So we're going to set end of word equal to true now, and then we don't really have to return anything. So that was pretty simple.
Then you return that probably, or no?
Right? Not a lot of complex code. We did have to go through every character, and we either created nodes or just iterated through those nodes. And the remaining two functions, search and starts with, are actually going to be very similar to this insert function. So now let's get started on search.
So I guess the other one is pretty much the same. Also self dot or cur. I need to understand this cursor better. I think I'm just gonna copy this stuff here and modify some. What I think needs to be modified. So here it should be return false, I think, because it doesn't exist. Yeah, that's pretty much it. And then in the outside should be how I'm gonna check for the end of the thing. So maybe I'm missing something on this one. In the end. Oh, I forgot to erase this. Hmm. Oh, I think I get it now. It's like the current node. So it updates the children based on whether or not it already exists. So probably the reason why I can't do this is because I'm only searching for the current roots, and the words can exist on different roots. So how can I figure out? Yeah, I have to update, right? You're talking about this one? But then if I do like this, maybe it works. I don't think it works because in this one you can do this because you're updating, but on this one it's not necessarily the case that if it doesn't exist here, it's gonna be the top one. That's the issue. Oh, damn. Yeah, let me just look at this one first,
So
and
we
then
wanna
I'll look at the solution for the other one.
search to determine if a word exists or not. So just like the previous function, we're going to start at the root node, so self.root, and we're going to go character by character in the word, and we're going to check if this character exists in our tree. If it does not, so if C not in current.children, if this character does not exist, then what do we have to do? We return false, meaning the word just simply does not exist. If it does, then we can move ourselves to that child node. So we can update cur and set it to the child node of that character. And then we're going to basically keep doing this for every character in the word. If the word doesn't exist, we'll return false. If the word does exist, that means the entire loop will execute, and then then cur will be the last character of the word, and we know that it is a word if cur has the end of word variable set to true. So this is the variable we're going to be returning. If this is
So
set
it does do the same thing. Oh, and then he returns end of the word. Smart. Because that's how you check if the end is the same. Because otherwise you're not capturing the full word, I think. But I'm not sure if this is gonna pass. Maybe there's something different with this one that I just don't understand. If there is any string in the data structure that matches word or false. Otherwise. So maybe, what if but if I return true here? Or maybe this passes? No, the problem is I'm returning false on the last two ones. Yeah, I'm just gonna look at the solution, because I don't want to waste a lot of time on this. I think it's this one. Choose is end of the word. I tried before, but it didn't work. The name of the field.
Hey everyone,
you
welcome
mean
back, and let's
here? I did this and it doesn't work also. This here. I guess the difference is this in this one is that you are checking if the string exists. It doesn't necessarily need to be the whole word. So maybe the prefix
the
one
true.
is
That
the
means
same.
this is a
Let
word,
me-
and we'll return the children right now.
This starts
Then we
with
will
function.
return prefix itself is.
Yeah, but it just returns true as well. So don't forget, search returns a boolean, true or false. Yeah, but if you return this value, it should be true or false as well. Right, because here it's true and then here's false. So it is a boolean, I think. Even if you do true here, it doesn't work. I think there's something that we are missing about the way that the problem is phrased. Because also it doesn't make sense for him to put two problems that are exactly the same in the list. So there's probably something different about this one.
Let's write some more neat code today. So today let's solve design, add, and search words data structure. So this is another problem from the blind 75 LeetCode problems list. So this is the spreadsheet I've been using to track which videos we've uploaded for those 75 problems. You can see that most of the solutions have already been updated. And today we are working on this problem, a tree problem, add and search word. So basically another day, another problem from this LeetCode blind 75 list. The link to this sheet will be in the description if you do want to take a look. So basically we're designing a data structure to efficiently solve this problem of basically adding words. We're taking new words, adding them to the data structure, and also we're being given words and we want to search to see if those words match any previously added words to our data structure. So we only need to support 3 functions for this data structure. One is just going to be the constructor that's going to initialize the object. One is going to be adding a word, and that one is pretty self-explanatory. So we're just given a string, a word, and then we're adding it to the data structure. Now this word could only consist of lowercase characters from lowercase a to lowercase z. And the third one is going to be the one where the bulk of the algorithm is going to be contained. So this is going to be searching words. So we're searching a word, and the word can contain any character from lowercase a to lowercase z, but there's one additional character it could contain, a dot character. And what we're told is that the dot character is actually like a wildcard. It can basically match any character in the string. So for example, let's say in our word list so far, let's say we had just a string a, b, right? So this is what we have so far, and we're trying to search dot b. So basically, would this search match any words that contain so far in our data structure? The answer is yes, because the dot would match any first character, right? So we basically match this lowercase a, and then we do have an additional b, which matches the second character in the string. So a dot matches any character. That's what's going to be tricky.
That's the difference probably. Let me see if yeah. So here you probably need to check and see different than dots, maybe. Mm. But then, oh, okay, let's try like this. No, it still doesn't work. So I'm just gonna look at the
for us
solution.
to implement. Now, the brute force way to solve this problem is pretty simple, right? We would basically have a list of words, and then just for every search, we would just say, okay, does this search match any of the words in the input list? Now, that's not going to be super efficient. A more efficient solution is going to require a trie data structure, aka a prefix tree. So this is what we're going to be using to solve this problem efficiently. I will say, if you've never heard of this data structure or you've never implemented it before, you basically don't have a chance of solving this problem efficiently. But if you have heard of this data structure, it's pretty intuitive why this data structure is used in this problem. Basically, a prefix tree, right? So for example, if we were searching B dot dot, we would want to first find all words that start with the character B, and then check, are there any of them of length 2, because the remaining portion of this can match any string of length 2. So a trie is basically a tree that has some kind of root node, and each node can have up to 26 children in this example, because we have lowercase characters from A to Z. So basically, each node is going to represent a single character, right? And then each node could have up to 26 additional children. And basically, a word in this case, for example, this is A. If I had a B here and then another C, this is going to be a single word, right? And so if we inserted the word, let's say we added the word ABC into our trie, this is basically how it would look like. Now, one additional thing we have to say is, for a particular node such as C, we have to say this is the end of the word, right? Because what we're trying to say is we did not add the word A, we did not add the word AB, we've only added the word ABC, so we have to designate that this is the last character. Now, if we added another word, for example, AB, what we're going to do, we're not just going to repeat that. We're not just going to say, okay, now there's going to be a lowercase a here, then there's going to be a lowercase b. Notice how we already have those characters available to us. We're going to reuse these characters. So instead, what we would do, adding this word, we would say, okay, let's add an A. So let's start the root, add an A.
I'm gonna skip this because
3 words, all of them end with a D, but they all...
it's repetitive.
Now, last, we didn't find a match down this path, and we have a pretty small trie right now, but it's possible we could have a really... One thing I like to do for trie problems is just define a trie node, because it's going to have a couple variables. So in the constructor, we're basically going to initialize 2 fields. So for this
And this
trie
one's
node,
probably the same
nodes
as the
children,
previous.
if C is not in there, then we need to obviously insert it, right? So what we would do is say current dot children of C is going
Probably
to
the
be
same as
a
well.
I. And so remember, this character
Yeah, okay. Word.
could be any character from A to Z, in which case the problem would be straightforward, right? We would just search our trie and see, does this character already exist? And then we'd continue. If it doesn't already exist, then we would return false. But we know this character could actually be a dot character. That's what's going to make this tricky. So if C equals a dot character, the else condition is if it is a regular character. Now let's start with the else case, because it's a little more simple. So if C is just a regular character, what are we going to do? We're going to check if C is not in current.children. That means this character does not exist. We needed this character to exist. We're searching for this word, but this character doesn't have any of the 26 characters. And we can't really do that iteratively very easily, right? We are going to use backtracking or recursion to help us do that.
Yeah, no for the first question, and kind of for the second one. I don't really believe in preparing for job interviews. It's not the way that I like to think, because I think it's counterproductive. You can't really control if you're gonna get hired or not. So I think it's a better way to look at it from a standpoint of improvement. So the main goal for me is to improve as much as I can, and then also I'm looking for jobs. So I think a lot of people make this mistake of doing these challenges just for preparing for job interviews, which puts you in a mindset of memorizing stuff, which is not good. I think it's better to think about becoming better at thinking in a way that allows you to become better at developing applications and stuff like that. But I'm a super beginner. I started these data structures and algorithms pretty much less than a week ago. So I did some Code Wars before, Code Wars challenges, but I had no idea about data structures. So the way that I solved the challenges was pretty much finding a way off the top of my head, or thinking really hard about the logic, but I didn't think about it in this way of data structures. And what made me switch to LeetCode is that I had a problem that was really hard for me to solve. And then I asked for another guy that streams on Twitch. His nickname is Kiki Impact. And I asked him for him to solve it, and he solved really fast. And he used something called a heap to solve the problem. And he does LeetCode for the most part. And then I realized that I think LeetCode is probably a lot better than CodeWars to learn this kind of stuff, because it's more focused on the principles behind it. And CodeWars is more like a freestyle thing. So it's probably better to focus on LeetCode for beginners and then move on to other sites if you feel like it. And then that's the reason why I decided to do LeetCode now. I want to become good at this and then continue to do the projects that I'm working on.
That. So for example, let's say we had a string like .ab. What we would want to do then is say, okay, it could match any of the possible characters. So what we would say then is we would go through for every child in current.children values, because remember, for current.children, that's a hash map, and then we want only the values because those are going to be the actual children. So because we know the dot could match any character, so for this dot we would basically match every single character, and then we'd say, okay, for each of these we want to do the recursion on it, so we want to do the depth first search on this. And when we're actually doing that depth first search, it could just be an iterative matching. So what I'm trying to get at is that this entire thing that we just wrote is the recursive function. This is the depth first search, right? We have the iterative portion here where we don't have a dot, and we have the recursive portion over here where we do have a dot. So let's wrap this entire thing inside of a depth first search function. Depth first search, DFS. And so let's just tab it over. So now let's think about it. When we're doing our depth first search, what are we going to pass in? Well, we want to know what's the remaining portion of the word that we are trying to match, right? So we would want to pass in the index. So let's call that J. We're passing in the starting index J, right? And the other thing we're passing is what's the current root or the current node in our trie that we're at. So in this case, so depending on which one of these we're iterating through, we're going to pass in that child node, right? So that's what the node that we're going to be passing in, whatever child that is. So that's how we're going to call DFS. So let's define that up above. So J is going to be the index parameter, and let's call...
Yes, that's why I like LeetCode as well, a lot more than I did with CodeWars. I don't really remember why I started doing CodeWars, but I think was kind of like the same thing. I wanted to improve, but I didn't know really well what to do. I wanted to improve on algorithms. And the thing about LeetCode is that it focuses a lot more on these fundamentals of data structures, which is more... So it's more about solving problems to understand the thinking behind building the systems, instead of just solving problems for the sake of solving problems. I think I don't really like that. And it's something I noticed as well. Even when I was just starting, when it feels like you're just doing a problem that you kind of know how to do it, or it's more like figuring out the mathematics or something like that. It just feels like a waste of time. Like, why am I even doing this? But the cool thing about LeetCode is that it's easier to see the connection with that and real world applications, if that makes sense. And I think at the moment I stop feeling that connection, and I feel like I'm just doing these problems just for the sake of doing them, I'm probably going to stop. Or if I'm not able to see a correlation with how many of these problems I solve and how much better my thinking is when I'm building stuff, then I don't really see the point in doing this.
what the node that we're passing in is. So, okay, so current is, instead of being called self.root, it's actually going to be initialized to the root that we end up passing in. And okay, so here I passed in j, but what we would actually pass in is going to be I. Actually, not just I, but I plus 1, because we're going down a child. So we're going to pass in I plus 1 as the index of the character that we're looking for, right? Because what we're saying is we're skipping the dot, so we're going to have to increment I plus 1. And this function is going to return a Boolean. So if this function ends up returning true, that means we found one path that matches. And remember, if we find a path that matches, we return true immediately. We're done. We don't have to do anything else. If we don't find a path, we're going to keep going down all possible paths until we do. If we never find a true, if we never find a match, then we're going to return false. Oh, and one more thing. So initially up above, we said I is going to go through range of the length of the word, but we know we could be starting at a different position. Here, we're always going to start at 0. We don't want to do that. We always want to start at j, whatever it happens to be. So that is the main recursive portion. And the last thing is, let's say we were given a word ABC, and let's say we found a match, right? We didn't have any dots in here. What would that do? Well, we'd go through the for loop. We'd always execute the else condition, and we would always find the current node, and then the entire loop would be finished. Then what would we want to return out here? Well, we would want to return whatever current happens to be. So if current.word is true, then we would return true. If current.word was false, then we would return false. So we can just leave this as it is. So that's the main portion of this algorithm. The last thing that we want to do is actually call this depth first search function, right? So what are the parameters that we're going to give it? Well, we're always going to start at index 0 because we're going to start at the beginning of the word, so we can pass in 0 for j. And we're always going to start at the root node of our try, so we can pass in self.root as the root node, and then we would just want to return the result that this DFS function returns. So as you can see, this function did work, and it does work pretty efficiently. So if you didn't already know what a try was, I hope that you learned that today. So this is the entire code. And if you did already know what a try was, I hope that you learned a new application of it. So I hope this was helpful. If it was,
And so this one is a lot more complicated than the previous one as well. And it does the first search reversal. The else is the same, but the other one is checking for the values and then calling recursively with I plus 1. So pretty much should increase the loop. So it's pretty much the same thing as iterating, but because the I is gonna renew every time if you don't make it, if you don't sum, then it does it like that. And then passing the child. Yeah, I think I sort of get
please
it.
like and subscribe. It supports the channel
Yeah.
a lot, and I'll hopefully see you pretty soon.
So this
Thanks for
one's
watching.
the next one's probably gonna be impossible to solve, but I think I will be right back before I start this one. think I'll do 2 more. It's already late here. Yeah, I'll do this 2 more. And then I'll read the Ethereum stuff. And then, like I said before, tomorrow I think I'm gonna do this. I'm gonna just record myself doing instead of streaming. And I'm gonna keep it short, each one of them, and read the book in between challenges. And hopefully I can finish the list fast, so I can focus on the things that I feel like I'm lacking. Given an m times n board of characters and list of strings words, return all words on the board. Okay. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once in a word. The same letter cell may not be used. Okay. And the list of string words, they're all words on the board. God damn. Yeah, this one's it's gonna be extremely difficult. Or maybe I can just transform the board into a tree. So maybe I should start by doing this. So let's think. So if I transform the board into the tree, I can just look it up using the same function as before. The same function on the previous challenge. I think I kind of forgot. No, let me see if I remember. So you have self, you have words, then root is gonna be a tree node for C in words. Yeah. If C not in roots dot children, return false. Oh, it's actually current. Yeah, but it's slightly different, so it's probably the same thing. Root C. Or root children C. Maybe I should apply the same class. I should apply the same functions on the class and then just transform the board into the tree by looping through the words. Yeah, that's probably the best way to solve this. Not the best, but easiest. The thing is, I think I still don't remember really well. So currents. Because there was self.root as well. Oh, it was 2 classes. That's the thing. So there's the node and the tree. Why is this giving me this? stuff here. Can't I create 3 classes? It's pretty much the same thing here, I think. Currents, dot children. See. And then return currents dot end words. And then there was the insert function. I'm just gonna call it add words. And it's pretty much the same thing. Yeah, the difference on the other one was the dot, so this one doesn't have the dot. It has a special character. Now I don't remember how to add on the thing. I think it was equals C, but I don't remember really well. Or C equals this. I think it's equals C. Because I want to make the key value equals to the, let's see, the letter. And then I move the current to another children. And then I don't return anything. And I also need to add currents dots and word equals true. And then on this one, I would just so each list is gonna contain a word. So I can just write item in words. And join each character and make it go to a word. And then I pass into the function. Oh, actually, let me see. Yeah. Because I'm gonna add and then I'm gonna call the search function. Oh no, I need to return the words. That's why it's different. Yeah, I need to add the characters instead of the words on the thing. But how am I gonna know what is a word or not? That sounds impossible. Because the only way to add character by character is if I know the words previously. Oh, no, maybe I'm correct. Oh, they give you a list of words and then you need to find which words exist on the bar. So maybe the way that I'm adding here is incorrect. And they also need to be adjacent. Yeah, so the first thing would be to add the words in the list in this class here, the tree, and then search for the combinations of characters to see if it matches. So a word can't be diagonal, so I'm thinking about creating an object and making a list of the horizontal words. But that doesn't change anything. Yeah, the only way would be to do two nested for loops, which is not good, that I can think about. So I can search horizontally and vertically for all possible combinations of letters. So do a nested for loop, make if else statements, and then you call the other class to see if the words exist. And maybe there's a way to translate the board into a tree node as well. And then you create two different trees or tries, and you compare both of them. Okay, I'll look at the solution probably. So two different ways that I thought about, and I'm not sure if it works, is the one creating two different tries and then comparing them. Other one is adding the words into the try and then running a nested for loop on the board and then comparing based on if else statements to see, searching the tree to see if they try to see if they exist, if any words exist with these letters. I think the only thing that I would have to change would be the search because of the order of the letters. You'd have to test for all the other orders possible. There's probably a better way to do this than to just get all the combinations I suspect. Based on the logic of how the words are inserted in the try. Because of the stuff we said before, where when you add a letter, you don't need to repeat it, so you can just continue. So I assume it would be something like that using that logic. Yeah. I should lower down the volume there, the music.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve word search 2. And once again, like usual, this is a problem from the blind 75 LeetCode list, a list that we have been tracking on this spreadsheet, and the link will be in the description to this. And we are very close actually to being done with all the major problems on this list that I wanted to do. And probably at some point I will finish up some of these easy ones, like contains duplicates. I think that's a pretty trivial problem. Don't know how many people are waiting for a solution on that one, but I probably will do it eventually, just for the sake of completeness. So this is word search 2, and word search 1 actually we already solved on this channel, and that is LeetCode 79. So I do recommend understanding that problem before you try to do this one, because this is definitely an extension of that one. So we are given an m by n board exactly the same as we were in word search 1, and we are given a list of words this time. Previously we were just given a single word, but in this case we're given a list of words, and we want to know from that list of words which of those words exist in this board, and whichever ones do exist we want to return those words. So previously we only wanted to know if one word existed in here or not, so we returned true or false. But in this case we want to know how many or exactly which of these words do exist. So if we just reuse our solution from the first word search, what we're going to do is we're going to go to every single position in this grid, and we're going to start a depth first search recursively on here. So it's just backtracking, right? We're going to be checking brute force what's every word we could come up with, right? So starting at O, could we come up with a word in our list of words, right? So we just go in all four directions basically, right? So if we go here, we'll get OE. If we go this way, we'll get OA, right? Et cetera, et cetera. We could, possibly make a word like this, OAAN. Or we could make a word like this, O-A-T-H, and this happens to be a word in our list of words. So we would say, okay, O-A-T-H, this is a word, so this is going to be added to our solution set, so it's going to go in the output. So a very brute force approach would be, so for every single word, we're going to run a depth first search starting at every single position and check, okay, could we make the word oath starting from here? Could we make the word oath starting from here, et cetera, until we get, all the way to the bottom of the grid. And we have run a depth first search on every single position. Now that's not going to be super efficient, right? And then we're going to have to do the exact same thing for the next word P, right? Because maybe this word could exist, so we'd have to brute force check every single position, et cetera, et cetera, et cetera. And one way to analyze the time complexity of that would be something like worst case 4, and 4 because that's the number of directions, from any position we could go in 4 directions. Now we can't revisit the same position twice, of course. So basically the length of our depth first search is going to be the dimensions of the board. Let's call that m by n, right? So that's how much one DFS would be, and we're going to be doing a DFS starting at every single position. So it's going to be something like m by n to the power, or m by n multiplied by 4 to the power of mn, and we're going to be doing this for every single word. So basically, let's say W is the number of words, so this is going to be super inefficient. Now there is a way basically where we can make this more efficient, where we can get rid of this constant W. Basically, the solution is going to be, we're only going to have to run DFS starting from each position a single time, because as we're checking, what are all the words we can create starting at this position, right? Starting at this character A. What are all the words that we could create? Now, the main idea that we're going to be doing, instead of just checking a single word at a time, like running DFS on here just to check if this word exists, let's check simultaneously. Let's check all the words in our set, which of them can be created starting at this position. So that's the idea we're going to be using, and we're going to be using a data structure, which is going to be very useful for it, because what we're going to notice is we can check all words starting at here based on the prefix, right? So clearly here, we only want words starting with the letter A, right? So the prefix is going to be A, and what kind of data structure can help us organize these words based on their prefix? Guess what? Either you have heard of this data structure before or you haven't. If you haven't heard of this data structure, then you probably don't have a chance of solving this problem in the optimal way. So I would learn what this data structure is first, but if you do already know it, the solution is actually not too bad to implement. So the data structure we're going to be using is a trie, aka a prefix tree, which is going to help us organize these words based on their prefixes. So let's say we had a pretty small grid and we had a pretty small list of words. The words are app, ape, and ace. So we want to know which of these words can be found inside of this grid. Now let's use the idea of prefixes that I mentioned. So let's say we're going to start our DFS here, right? So this is the first position we're going to be at, and we can't revisit this position twice. Makes sense so far. So far we have a single character, right? We have found the character A, right? So we can basically, we want to know all the words that we could create starting at this position, DFS from here. And of course, then we're going to repeat that by doing a DFS from here, here, and here. But so far we're only starting here. And of our entire list of words, we want to know which one of them have a prefix of A. Because if we had a word such as bat, then we'd say, okay, bat does not start with an A. So basically we don't even have to consider that, right? We don't have to run a DFS on here searching for the word bat. It doesn't even exist in this position, right? The letter B does not start here. So what we're going to have to do is basically go through every single word. This word starts with an A, this word starts with an A, this word starts with an A. So potentially so far, all of the words could be found starting at this position, right? So we haven't eliminated any of these just yet. So now let's say we go down first, right? Of course, if we go up, that's out of bounds. So we're just going to return there because we're going to see, okay, it ended with the word A. A does not
exist in our list of words, so of course we're not going to do that. Of course, if we went left, that also would not work, but we can go down. So let's start going down first. So we add a P to our word so far. So far we have AP. So then again, we're going to have to just go through every single word, check, okay, does this start with AP? Yes. Does this start with AP? Yes. Does this start with AP? No. So we don't want to consider this word anymore, right? But as you can see, this is going to get kind of complicated, right? We're having to go through the list of words every single time. That's not really helping us out in terms of efficiency. A more intuitive way would be if we could check the prefixes of these words more easily. And of course, we know a data structure, prefix tree is exactly what that is for. So basically what a prefix tree is going to be, it's going to be, every single character is going to be a node. So one node is going to be A, and we're just going to take these words and add them to our prefix tree. So we want all words starting with the character A to go here, right? So let's add childs of these. So what characters come after A? Of course, we have a P and then we have a C. So all words that start with AP are going to go down here, and all words that start with AC are going to go down here. And how many different words do we have that start with AP? We have app and we have ape. And all words that start with AC is just one word, ace. So do you see how this tree is organizing these words based on the prefixes? So now we started at A, right? We want all words that start at A. So this is where we're going to be at so far. And we see that, of course, there are 3 words that start with A. And by the way, let's say AP, this is not a word, even though it is a path in our trie, because basically, let's just say we call these 3 leaf nodes happen to be the end of words. It's possible that we could have a word AP, but in this case, we don't up here, right? We don't have AP, so this node is not going to be marked as the end of a word. So only these 3 are marked as end of words. But so now when we go down in this direction, we go to a P, all we're going to do from this position is check, does this have a child P? If it does, we're going to say, okay, let's go there. So now this is going to be all words that potentially start with AP, so this prefix. Now, if we did not have a P, right, then we would say, okay, we went down here, AP, we don't have any words that start with AP, so in that case, we would just return. That's our base case, right? If we didn't have any words with a prefix of AP, which we could check pretty easily with this prefix tree, we wouldn't want to continue going down this direction. So you can see that we're making things a lot more efficient for us using this trie. So now from P, we can't go down, that's out of bounds. We can't go left, we can't go up because we already visited that position. So we can go right, which is going to add the character E. So from here, from this P, we want to check, do we have a child E? Well, this is not the E, this is though, right? Okay, so far we did find a path in our prefix tree. Now let's check, is this the end of a word? Since it's marked purple, that's what I'm just indicating. So yes, this is the end of a word. Therefore, we found a single word down this path that we were maintaining called A, P, E. That, yes, you can see it's found in our list of words. So therefore, we found one word that we can make from this grid that, can be found basically. So we're going to add ape to our results. Now from here, we would want to continue. Now we can't go right, we can't go down, we can't go left because we already visited there. So we would go up. So we'd say, okay, add a C, right? So from here, APE, and then we add a C. Does this word exist? Well, this does not have a child of C, so of course we can't do that, and that makes sense because this word APEC does not exist in our input list of words. So therefore, at this point, we would return because we don't even have any words that start with this prefix. So far, we did find one word, ape. Now, when we started here, the first direction we went was down, but it's possible we could also go right, so let's do that. So now we have AC. So we started here, we checked, does this have a child C? Yes, it does. It's over here, right? So now we can't go right, we can't go up, we can't go back left, so now we go down, ACE. Do we have a E child under this C? Yes, we do. And this is the end of a word, right? It exists in our list of input words, so now we found another word, ace, and then we would continue from our grid in the only position we can go to, which is the P, right? So we'd add a P, we'd say, okay, does this E have a child? P, it does not, so therefore we can't continue, so that's going to be our base case, but it's okay because we at least found one word, so we can go ahead and add that to our list of words, ape and ace. So now is going to be the easy part. So we started our DFS from this position. Now let's start the DFS from C. So we look in our prefix tree. We do have a prefix starting at A. Do we have a prefix starting at C? We don't. So immediately we can say, okay, we know for sure none of our words start with the character C. We didn't have to run through the list of words to do that. We just did that in an O of backtracking DFS, which you can learn from. So now let's write the code. So the first thing I want to do is actually implement a trie node class, or a trie class basically. And so in the constructor of this, if you have written a trie before, you'll know that there are mainly 2 things that we worry about for a trie node, and that is its list of children. So that's going to be one member variable for this class, a list of children. Now you could use a list. In this case, all characters I think are going to be from lowercase a to z, but a more generic way to handle it is just using a hash map. So the key is going to be the character, and the value in this hash map is going to be the child node, the child trie node. And also for each node, you want to be able to mark if it is the end of a word or not. So one member variable for is word, it's going to be a Boolean. Initially, we can set it to false. Now to our trie, we are going to want to add words to it. So let's define one function, add word. And this is really going to be the only function. So we'll be passed in a string, a word, and we just want to add that word to our trie. So let's get our current pointer to be at the root node, which is just the self node. And then we're going to go character by character in this word and just start adding them. Now it's possible that the character might not exist in our trie node. If it does not exist, so if C not in current.children, if this character does not exist, then we're going to obviously have to insert it. So current.children, at character C, we want to create a trie node for this particular character. If it already exists, then we're going to
so I made it equal to C. I forgot about that. Is equal to the trie node.
skip this if statement, and simply we're just going to move our current pointer to that position. So current.children at
character C. So that's the try node that we want. And at the end, all we have to do is return the current pointer. Or actually not return the current pointer. At the end, we have to mark that this is now going to be the end of the word. So the last character that we ended at, current, is word. We want to set that to true when we insert a word. Now, the reason we're not going to define a search function, like searching a word in this try node, is because we're going to be doing that simultaneously as we do our depth first search on the board. So now let's start getting into the DFS. Or actually, the first thing we're going to want to do is create a root try node. So let's create a try node with the class that we just defined. And for every word that we're given in the input, so for W in the list of words, we just want to go ahead and take each word and add it to our try. So root.add word W. And now we can start going ahead and doing the depth first search. So first I like to do is get the dimensions of the board, so rows and columns. We can get the length of the board. We know for sure that the board is going to be non-empty and the list of words is going to be non-empty as well. They do tell us that in the problem description. Now I'm going to create two sets, result and visit. So result is going to be the set of words. It's possible we could visit the same word twice inside of our board, so we don't want to have to return duplicates. And the visit set is pretty self-explanatory. When we run a DFS on the board, we don't want to get stuck in like an infinite loop, or mainly we don't want to repeat the same character twice. We're not allowed to do that. So once we have those defined, we are going to define a DFS recursive function. We're going to be going through every position. So we want to pass in the coordinates, row, column as the coordinates. We want to pass in the current node that we're at in our try, depending on what characters we've already visited before. And we also want to pass in what is the word so far. So for example, we visited two characters, AC. We want that to be stored in this word variable. And of course, if the node that we're visiting happens to be the end of a word, what we're going to do is just take that word and add it to our result, which is out here. We don't have to pass it into every recursive call. So for this DFS, let's go ahead and define the base cases. So of course, if we go out of bounds, row is less than 0, or column is less than 0, or row is too big, meaning it's the number of rows, or column is too big, meaning it's the number of columns, or maybe this position, row column, is already been visited. So if it's already in visit, then we're going to return. Or maybe the character that we're at, for example, board at position row column, maybe this character is not even in our try. Maybe it's in bounds, right? But it's not even in our try at the current position that we're at in our try node, right? Meaning this character is not in node.children, right? If it's not in the children of the current node that we're visiting, that means this character doesn't exist in our try. Therefore, it's not one of the words that we were given in our input list of words. So if any of these are true, then we're going to return. That's our base case. If that's not true, first thing we want to do is make sure we mark this position as visited. And after we're done, the last thing we do before we return is we're going to have to mark this as unvisited. Basically, since this is backtracking, we can't visit the same one twice, but once we're no longer done visiting it after we return, then we can go ahead and remove this position from being visited. So since we got to a new character, we want to update some variables. So we want to update node. So node is going to be set to node.children of the current character that we just visited, which is board at position RC. So we're updating the node because we know that that node does exist. And we're updating the word, right? So we're taking the current word, adding to it the new character that we just reached, board at RC. And before we do the recursive case again, before we look at the neighboring positions, we do want to check, is this the end of a word? So we can check that based on our node. So if node is word is true, then of course we can take our result and add to it the word that we just built, right? The string itself, not the node. We're not going to add the node to result. We're going to add the string word. So this is just basically, checking if it actually is a word in our list of words, and we're, doing some bookkeeping here. And once that is done, we can go ahead and actually do our recursive case. You could write it with a loop, but I like to be lazy, and I think it's pretty okay to just copy and paste DFS 4 times. So we're going to pass in the coordinates, and we're going to pass in the node, and we're going to pass in the word that so far we have built. So let's just copy and paste this 4 times, going in each of the 4 directions, up, down, left, right. So all that, we have defined our DFS function, about 15 lines of code. So remember, what we actually wanted to do with that DFS is go through every single position, every single starting position in the grid. So I'm going to do a quick 2D loop, or quick nested loop on the entire grid, and call DFS from each starting position in the grid. Now for node, what are we going to pass in? We're going to pass in our root node that we defined up above. And for the word, initially, it's going to be empty, right? So that's what we're going to pass in for the word. Once that is all said and done, we want to return our result. But don't forget, our result is a set to eliminate duplicates. We can cast it into a list pretty easily in Python. So that's what I'm going to do. As you can see, this is the entire code. So this is the entire code in all of its glory. So this, you can see that this solution does work. Once or twice, it actually did give me time limit expire. I think there is a slight optimization that you can make to this problem. I don't think it actually improves the overall time complexity. But once you find a word in the try, basically what you can do is actually remove that. If it's a leaf node, you can remove that from the try. because you don't have to search for the same word twice. That's a slight optimization that you can make, but I think this solution is mainly good enough, and it's too big to even fit on the screen. That's how you know this is a hard problem. No matter what you do, it's going to be a lot of code that you have to write. But I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
So I think I'm not gonna do this next one today. Probably gonna do it tomorrow because I'm not sure if I'm gonna have enough time to finish reading these articles from Solidity smart contracts. Or maybe to read this stuff, I'm gonna use these modes probably better. I'm gonna see, because I remember last time I read this, it took me a while, probably 2 hours or maybe even more. So I'm gonna see if I can finish, ideally I can finish this today. I'll be right back then, start reading this. Also think I'm gonna put some music behind. Be right back. So I think I'm gonna run this script that I have here. Yeah, last time the power went off and I don't remember. I should probably improve this so that each time that the script stops, it remembers the block number. And I can use a pickle file for that, I think. But I don't care enough about this thing to do this. Once I have a decent amount, which I think I already have, but probably 10 million is gonna be better. So I think once I have 10 million blocks, it's probably already enough to do a bunch of stuff, a bunch of analysis, or to transform it into SQL or any other format to continue this project here. And then if I do decide to make the full website, then I'm probably gonna think about writing this in a way that I put this number in a pickle file and then it loads each time I run the script. It saves the last time and then runs again. I'm gonna put some music for myself in the background while I read the articles. The last article We saw how the function selector acts as a hub or a switch of sorts in our basic token.sol contract. It sits at the entry point of a contract and redirects execution to the matched function of the contract the caller wants to run. If the total supply function is called, execution will be redirected to location 91, balance off to 130, and so on. Now let's start a new debugging session in Remix as we've done before and call the total supply function again. Make sure to always expand the instructions panel where the heart of Remix debugger is. As we saw before, Remix will place you at instruction 346 where the function's body is just about to be executed. Last time we took the transaction slider from this position back to instruction 0. Because we wanted to study the contract's entry point and how it got to the function's entry point from there. This time we're also going back, but to instruction 91 instead of instruction 0. Because there's this thing that Solidity uses to wrap a function's body. Don't worry, we'll get to the function's body soon enough in the next article. We're almost there, your patience will be rewarded. So step back to instruction 91, which is where the function selector leaves us, because the function ID matched total supply. At this point, the stack should only contain the function's ID. Now let's walk through the code from here. Okay. Jump over this or reverse, jump that. Instructions 92 to 103 will basically revert if there is a value, i.e. ether, involved in the transaction. 92 and 103. 92 to 103, okay. Because of this thing here. Again, this is a very common structure injected by the Solidity compiler whenever a function isn't payable. We saw this exact same thing being used in the constructor. And it was also a non-payable function. This non-payable check structure will check if call value is 0, and if so, we'll jump to instruction 103, skipping the revert op code in instruction 102. Okay, so this non-payable check structure will check if the call value is 0. And if so, jump to instruction 103, skipping the reverts. Also, I think guys is talking about the 98 here. Jump I. If you call total supply on Remix without setting any value, we'll reach instruction 103. Instruction 104 cleans up 0 that was left over in the stack. And then 112 and 245 are pushed to the stack. Execution immediately jumps to the later location, instruction 245. Notice that the jump occurs at instruction 111. And previously it pushed to 112, so it wouldn't be outrageous to imagine that the code is about to go do something somewhere and then come back that is. To remember where we left off, 112 jump and then return. Let's see if that's actually what happens by stepping to that mysterious 145 location. If you step through 245 to 250, you see that our theory was indeed correct. This something that the code detoured to is the actual function body. Whose inner workings are not important to us right now. What's important to the scope of this article is how the code reaches and leaves this body thing. That is how it wraps around it. It jumped into the body and not out of the body. So we see that the jump at 250 takes us back to 112. Okay, so this jump goes back to 112, as we so cleverly predicted. If this was Age of Empires, we should be hearing the Bronze Age fanfare by now. That's right, we're navigating through the bytecode using jump and jump I like crazy. Wanna play it? You deserve it. What is this stuff? It's just some sound. But there's something new this time around in the stack. The number at 10,000, the function body we just traversed was kind enough to put it there for us. If you were a smart contract, what would you do now? Please don't say I run away with all data. Remember that we're calling the total supply function. Somehow you need to get that value from the stack into a return OP code, so that it can be returned to the user. And that's exactly what the code does between the instructions 113 to 129, where there's an actual return OP code at the end. It will first read the current free memory pointer, instructions 113 to 116, and then copy the value that the body of the function placed in the stack to that free space, instructions 117 to 119. So copies here with the M star. The swap the M star, which ends up storing the number 10,000 in memory. See, we're getting good at this. If you don't believe me, just tap through the opcodes in Remix. It sounds complex, but it's not. Finally, the code will figure out the size of the data that needs to be returned. Let's look at that next. It first loads the memory pointer again and compares it using a subtraction to the previous memory pointer in instructions 120 to 124. Most likely in an attempt to calculate the size of the data to be returned. This value seems to be hard-coded anyway in instruction 125, which may seem redundant. It's probably the result of the optimizer realizing that the returned data size can be hard-coded to save some gas, and after applying the optimization, some residual opcodes are left behind. This is a perfect example of strange bytecode that apparently does nothing relevant or seems redundant. It's okay to ignore opcodes that don't seem to be accomplishing anything, and learn to live with them, or through them, let's say, and simply move on. As you read more and more bytecode, you start identifying the purpose of these generic, apparently hollow structures in sudden short bursts of enlightenment. That's enough esoteric nonsense for now. Let's get our feet back on the ground. I like the way that this was written. And this is by Open Zeppelin. Interesting. For now, let's get our feet back in the ground. Instruction 125 will push the number 32 to the stack. I'm not sure as well how close this is to actual assembly. I'm not sure if this is actually assembly or just something similar. I assume it's probably the same, but it might be a variation or something like that. Instruction 125 will push the number 32 to the stack and add it to whatever our magical offset was. From our previous generic calculation, which was 0 anyway, swap the values around to match the order which return consumes its values, and boom, the user has the total supply value returned. Okay, so we saw how the code was routed from the function selector into this wrapper structure that went into the function body, and out of the function body, and then dealt with the transaction of whatever the function body produced, and packed this data for returning it to the user. Now, shall we look at the other functions and see if we can observe a similar pattern in them as well? If you'd like to take a break first, though, this would be the perfect time for it. What we'll do next is simply reassure the structure we've just analyzed in the other two functions, with a little eye candy and a bit magic here and there along the way. So that's one function. To go, let's look at the balance of function next. It's strongly advisable that you have a quick look around in the deconstruction diagram to verify visually what just happened with total supply and to get an idea of what we're about to do with balance off. The function selector should take us to instruction 130, which is balance off's wrapper, and from there take us into the function's body and out of it, packaging the return value for the user. However, if you notice in the diagram, the code does jump into the function's body as expected, but it returns to total supply's wrapper instead of its own. Why? Not sure if I understand this part. So it should take us to 130. Also, from there, take us into the function's body and out of it. Package the return value for the user. However, if you notice in the diagram, the code does jump into the function's body as expected, but it returns to total supply wrapper instead. A tempting reason for this to happen could be that since total supply and balance off both return a unit 256 value, the chunk of code that grabs a unit 256 value from the stack and returns a unit 256 via memory is identical and could be reused. The Solidity compiler could be noticing that part of the code generated for these two wrappers is the same, and deciding to reuse the code to save on gas. Well, it actually does just that. And we wouldn't be observing this if optimizations were not enabled when we compile the contracts. Let's call this structure that's being reused the wrappers uint 256 memory returner. A nice exercise would be to compile the contract without optimizations and verify this yourself. Remix time, let's start a new debugging session by using the same address that we used to deploy the contract and call the balance off function. It should return the number 10,000 since the creator of the token initially holds all the goodies. The debug area step back to instruction 142, which is where the function selector left us this time. At instruction 144, 112 is pushed through the stack, which not surprisingly is the location of the uint 256 memory returner structure we just saw. The code's about to jump off to balance off's body. So 144, 12. Oh, so the hex is pushed to the stack, which is the uint, the same thing that is reusing to optimize. Code is about to jump off to balance off's body. It's remembering where to jump back to after the body is executed. However, the jump into the function body at instruction 175 doesn't happen right away. Something is going on before it actually makes the jump, between instructions 147 and 172. At instruction 147, hexadecimal number with 40 Fs, 20 bytes, is pushed to the stack. 40 Fs. And so this giant thing. Then a 4 dots call data load is called with the 4 as an argument. Okay, so it pushes and then calls, I guess, which has the effect of reading the first word of data 32 bytes from our call data after the function ID. If this sounds weird, then I'd recommend that you look at part 3 of the series, where we analyze how call data works. This word is the argument we passed into the function call, which is the address whose balance we want to check in the call to balance off. This address is masked with the big number for type checking masking. and then the jump instruction 175 is made to the function body targeted at instruction 251, with the address that was read from call data sitting comfortably in the stack and ready for use by the body. And so we witness that a function wrapper's job is not only to redirect into a function's body and package whatever comes back from the body for the user, but also to package stuff coming from the user for the function's body to consume. The function wrapper's nature does reveal itself to us in its full glory. A function wrapper is an intermediary that unpacks the call data for a function's body to use, routes execution through it, and then repacks whatever comes back for the user. This wrapper structure is there for all functions that are part of the public interface of a contract in Solidity. How this packing and unpacking is done is something that is meticulously defined in Ethereum's application binary interface specification, which specifies how incoming and outgoing arguments in function calls are encoded. Depending on how fast I finish this, I think I'm gonna still go back to the other problem and just spend 20 minutes on it before I finish this. Now let's have a quick look at the three function wrappers altogether. Hub wrapper. Okay. It's easy to see in a smart contract compiled by Solidity that the big chunk of code that comes after the function selector is the function wrappers, one after the other. And yes, the actual function bodies is the next big chunk of code that comes after the wrappers. And after that, there is this small peculiarity called the metadata hash that we'll also see in the future post, but that's it. We're beginning to see a grand architecture in EVM output produced by the Solidity compiler, and it's slowly becoming less mysterious, chaotic. When analyzing a contract's bytecode, you quickly learn to first try to see where you are in terms of this grand structure before you actually diving into the bytecode snapping details. So first comes the wrappers, then the function body, then the contract's body. I'm not sure. I'm probably not fully understanding everything, but I'm kind of getting. At least I'm improving my understanding. I feel like. I definitely feel like I'm improving, but not following every detail. Just probably something that comes more with practice, but or reading this several times. As we did in the previous parts of the series, we leave debugging of a call to the transfer function true. You should see how the wrapper unpacks true values this time, the beneficiary's true address and the value transferred. Sends that to the function's body and then grabs the body's response and packs it back up for the user. Makes sense, right? In the next part of the series, we will finally look into the function bodies. Once we do that, there's not really much else to do. Only a couple of details to cover, and we're done. This divide and conquer strategy is really starting to give us dominion over the problem we set out to tackle at the start of the series, which seemed overwhelming at first, but now is starting to become a pattern we can familiarize ourselves with. Next time you see an OP code, you'll not be scared. You look it in the eyes and firstly say, oh yeah, you and what OP code are. Okay, next one. Hey there, we've come a long way, haven't we? First, we understood the difference between a contract's creation time and runtime bytecode. Next, we understood how the entry point of execution from any call or transaction is routed to specific functions via the function selector. And finally, we saw how incoming transaction data is unpacked for a function to consume. And the data produced by a function is repacked for the user via function wrappers. In this section, we'll at last look at the actual execution of a function, or what we've been calling so far a function's body. A function body is precisely what the function wrappers detour through after unpacking the incoming call data. By the time a function body is executed, the function's arguments should be sitting comfortably in the stack or in memory if the data is dynamic, anxious to be used. Let's see this in action with the balance off function. This function should receive an address and return the corresponding uint 256 balance of such an address. Let's go back to remix and compile and deploy the contract as we've done before. And then call the balance off function with the address you use to deploy the contract as the argument. And then call the balance off function with the address you use to deploy the contract as the argument. Okay. So it's pretty much getting the balance off the contract that was applied. This should return the number 10,000 since it is what is initially assigned to whatever address deploys the contract in the constructor's code, which we used when deploying the contract. Alright, now let's debug the transaction. The first thing you'll notice is that the debugger placed us at instruction 252. If you look at the deconstruction diagram in the wrappers blue section, you should see that the balance of function wrapper redirects flow at instruction 175 to the jump dash instruction in 251. As we've seen multiple times before, remix places us precisely at the point when the function's body is about to be executed. So 251 jump dash. So this is the function wrapper, and this is the function body. And the last instruction here jumps to this one. Cast incoming call data into the address type. It may concatenate mapping position plus key and store in memory. Calculate storage position and read it into the stack. Now if you look at the stack, you'll notice that its topmost value is the address we called balance off with this one. The wrapper has done its job of unpacking the call data correctly, so we are ready to step through instructions 251 to 290. The body of the balance off function. Instruction 252 pushes a 20-byte value, which is the address, and uses the end OP code to mask the 32-byte address into its correct type. Remember, addresses in Ethereum are 20 bytes long, while the stack operates in 32-byte words. Also, pretty much it fills up the hex until it becomes 32 bytes, since I think since it is 20 by default. Instructions 274 to 278. The bytecode will upload the address from the stack to memory. It needs it there for the upcoming SHA opcode. If you look at in the yellow paper, the SHA-3 opcode has two parameters: the position in memory to calculate the hash from, and the number of bytes to the true hash. But why will the code be using SHA-3 opcode. This function wants to read from the balances mapping. More specifically, it wants to read the value mapped for the incoming address. If you recall how a mapping is laid out in storage, the hash of the concatenation of the variables slot, in this case 1. The hash of the concatenation of the variable slot, in this case 1, because balances is defined as the second variable. Total supply is the first, that's slot 0. With the actual key itself as the address. Is the position in storage where the value we are looking for is stored. We need both these values in memory to do its magic, and that is precisely what's happening here. So we've got the address in memory, but now we need the slot in memory. And that's what happens next between instructions 279 and 283. The number 01 is stored at memory position 20. Now memory holds the address at the first words, memory position 0. And the slot at the second word, memory position 20. Which you call 3. So it's called between instructions 284 and 270 and 287. Maybe I'll read this later. It's also good to go back to this stuff because of spaced repetition. So I remember the things I learned on the courses. By the time SHA-3 is called, instruction 207, the stack contains 0 superposition and 40 length for SHA. It's basically telling the EVM to hash whatever is in memory in the first two 32-byte words. 32 bytes in hex is 20, so 20 plus 20 equals 40. Now SHA-3 leaves the 32-byte hash in the stack, which is an awfully long hexadecimal number, considerably longer than an Ethereum address. This hash is the location in the contract's storage where the balance of the address passed to balance off is stored. So this hash is the location in the smart contract storage where the balance of the address passed to the balance of is stored. Okay, you can visualize this using the storage completely loaded panel in Remix's debugger. You should find a matching location in the second storage object. What's stored at this location? The number 10,000 or this number in hex. At instruction 388, sload takes the argument of where to read from storage hash and pushes to the stack. Finally, at instruction 289, swap1 resurfaces the function's wrappers jump last location, and a jump in instruction 290 takes us back to the outgoing portion of the function wrapper, which will repack this number for returning it to the user. I strongly advise you to go over the same debugging process we just did with balance off, this time with the total supply and transfer functions. The former is very straightforward, if not trivial, and the latter is considerably more complex but elementally made up of the same building blocks. The secret is understanding how values are read from mappings and written to mappings. There's really not much more to it. Now let's go back to the big picture. As we've discussed before, the function bodies are all packed together right after the function wrappers. The execution flow jumps to them from the wrappers and returns to the wrappers after performing each function's instructions. If you look carefully at the diagram, there's a chunk of code that comes after the function bodies called the metadata hash. This is a very simple structure that we'll look at next in the final part of the series. Update. This article initially contained mistakes and missed a few important points about the design of the metadata hash, which were pointed out by Chris from the Solidity team. Thank you. Among the corrections made by Chris is the fact that the structure is known as the metadata hash instead of the swarm hash. That the Solidity compiler is agnostic in terms of the system used to store contract metadata. Interesting. I should follow this guy. So I guess this is one of the people that made Solidity, or the compiler. In the last article, we noticed that the runtime bytecode generated by the Solidity compiler appends a strange structure after the function bodies block. You can see this in the deconstruction diagram or in the image below, referred to as the metadata hash. What exactly are these opcode doing? Notice the stop opcode as instruction 421. You may think that if there's a stop opcode there, whatever comes after it is basically unreachable bytecode, right? Well, not exactly. The code could be jumping over the stop opcode. However, there are no jump dash instructions after it, so that rules out the possibility of any execution reaching this part of the bytecode via a jump. In fact, if you analyze all the possible execution flows in this contract, which, believe it or not, is what we have done in this series, you'll see that indeed this code is totally unreachable. So why would the Solidity compiler append no executable code to its generated output? Actually, this isn't the first time that this happens. We've seen it before in part 2 of the series, where a constructor's argument were appended to the end of the creation bytecode. The code wasn't supposed to be executed by the EVM either. It was just there as a sort of hack to store the initialization values of a contract for consumption in constructors. Right, we still haven't answered the question of what this block of code is. To do that, let's walk through the opcodes and try to make some sense out of them, shall we? The first thing we see is a log1. If you look this opcode up in the yellow paper or in the Solidity documentation, we can see that log 0 to log 4 opcodes are used for logging events in the Ethereum blockchain, which makes no sense since we won't be executing any of this code. After that, we can see a push 6 of this and a SHA-3, a couple of invalids, a swap 10, a delegate call, etc. Invalids or something like that. What does that even mean? A total nonsense in terms of EVM interpretation. Clearly, looking at these bytes as EVM opcode representation is absolutely pointless. We need to look at this as raw byte data, which, as you remember, can be found in Remix's compile tab, details panel, runtime bytecode section, object property. The log1 opcode is really this byte, so the whole block of code at the end of the contract looks like this. Let's see how long. Okay, it's almost the end. The answer to this riddle can be found in Solidity's documentation in the encodings of the metadata hash in the bytecode section. Damn, there's a lot of things in the Solidity documentation, apparently. Maybe we should go through this documentation as well again at some point. The documentation is brief, but it gives us exactly what we need. I think I'm gonna close this for now. The compiler is hashing the contract's metadata, which includes information about the contract such as its source code, how it was compiled, etc., and injecting this hash into the contract's own bytecode. This metadata can also be seen in Remix's compile tab. Details panel metadata section. This hash can be used in Swarm as a lookup URL to find the contract's metadata. Swarm is basically a decentralized storage system similar to IPFS. The idea here is that some platform like Etherscan identifies this structure in the bytecode and provides the location of the bytecode's metadata within a decentralized storage system. And this part is interesting because I might have to use that at some point in the stuff that I'm trying to do. Identifies the structure in the bytecode and provides the location of the bytecode's metadata within a decentralized storage system. Which is this log stuff from the metadata. A user can query such metadata and use it as a means to prove that the bytecode being seen is in fact the product of a given Solidity source code with a certain version and precise configuration of the Solidity compiler in a deterministic manner. This hash is a digital signature of sorts that ties together a piece of compiled bytecode with its origins. If you wanted to verify that the bytecode is legit, you would have to hash the metadata yourself and verify that you get the same hash. And that's not all. The metadata hash can be used by wallet applications to fetch the contract's metadata, extract its source, recompile it with the compiler settings used originally, verify that the produced bytecode matches the contract's bytecode, then fetch the contract's JSON ABI and look at the netspec documentation of the function being called. This end-to-end authentication path built into bytecode generated by the Solidity compiler can not only be used to provide a user with information of the action about to be performed, but also to validate the legitimacy of such action. For example, if we look at the CryptoKitties contract in Etherscan, we can see that at the end of the page, Etherscan provides us with the contract's metadata address in Swarm, which was extracted from the bytecode in the way we've just seen. Interesting. You can look into Swarm's documentation to better understand this URL scheme. I imagine it's going to be similar to IPFS. And it doesn't have anything. Let's go back to our basic tokens bytecode and understand how Etherscan or any other similar utility for that matter actually finds the hash in the bytecode. As the Solidity documentation states, and this address and this will be rejected to the bytecode. In EVM bytecode, these two hexadecimal values would translate to log 1 and push 6. Now if we decoded the letter B as UTF-2 hex, we would get 62, Z would be this, and so on. You can see the whole thing decoded in the following diagram. So any application trying to find the metadata hash in the bytecode will look for these bytes at the end of the contract, this particular pattern, and extract the URL from it. Solidity uses a type of encoding. Thanks for the follow. Again, I should stop saying that, but yeah. Solidity uses a type of encoding called CBOR encoding. Concise binary object representation. It's probably some standard, or I don't know. Called CBOR encoding, with which not only the hash is stored, but the specific decentralized storage system and version used is stored. In this case, it's using Swarm's version 0 URL scheme, and that's why the structure contains the chars. These chars alternatively, it could use something like IPFS R0, indicating that the structure encodes an IPFS URL scheme. This makes it agnostic in terms of which storage system is used. It could be changed in the future, or we could even get to choose which storage system we want the bytecode to reference upon compilation. To retrieve the metadata file, we would have to connect to the same Swarm network to which the metadata file was uploaded to, using something like swarmgateways.net, or setting up a local Swarm node. Right now, this is something that is quite difficult to do because Swarm is still under heavy development and has not yet stabilized its hashing scheme, which can be seen is something being addressed by Solidity in this issue here. Interesting. No. So, is this your first time learning Solidity? I did Crypto Zombies, a bunch of courses on BuildSpace. I don't know if you're familiar with BuildSpace, but it's pretty much a site where they have a bunch of courses that they guide you through building stuff. Then I also followed another course on the Silo network to build an NFT marketplace. And then I made my own modifications to that NFT marketplace. And I think that's pretty much about it. And I also built my own node, my own light node using the GIF, which is not that hard to do. And read a bunch of stuff. And I also have started a project, and now I'm going to continue this project, which is analyzing data from Ethereum by getting the information from the blocks, and then I'm going to see if I can get the amount of transactions based on each address of each block. And yeah, analyze the data, run machine learning models on it, and try to display on the browser. But I'm not sure if I'm going to display it or not. I'm going to have to see, depending on how difficult it's going to be. And the reason I'm doing that is to integrate the blockchain with machine learning and learn more about Kafka and Spark. And I also read a bunch of stuff about flash loan bots and bots as well, MEV bots. And then the reason why I found this article was because I was doing a Ethereum speedrun stuff from this guy, which is really good, by the way, his channel, that I found on a course as I was doing the NFT marketplace, the course from LeetCode Camp. This guy showed up, and then I watched his videos, and then I found out about the Ethereum speedrun, which is a site that has a series of tutorials in a similar way that the other ones. And then as I was doing that, I found out about this article here, and then I decided to read it because I thought it was really interesting. Is pretty much talking about the assembly part of smart contracts, the compilation, the Solidity, which is done in U, I think. But I'll have to see these videos again because I didn't really get it the first time I saw it, I think. And they are really interesting, so that's why you caught my... Oh, okay. Yeah, but I'm not really a blockchain streamer. I kind of do everything, pretty much. I'm pretty much streaming just to show my progress. I'm learning how to program since the beginning. I started this, and I don't really have a thing that I do specifically. It's more just showing my progress, and then So then later on in the future, if I want to do something or if I end up building something, people can see the journey from the beginning. Hey, hello. Yeah, check him out, man. He's really good. And I like his enthusiasm. I really enjoyed his videos. It seems like a pretty smart guy. I'm good, and you? I'm almost at the end here of this article. It's a series of 6 articles. And I think I'm gonna read more stuff about this because it seems really interesting. Learning about the assembly from both Solidity stuff and assembly in general. Because I think it probably helps you to become a better programmer. Got accepted for a blockchain internship and thought about doing the same, possibly streaming my progress. Yeah, you should definitely do it, man. It helps a lot to focus, I've realized. But it can be a double-edged sword as well. Because it's more difficult to do things when you're streaming, obviously, because you are aware that everything that you do is going to be recorded and people can check it out. So it's a different kind of state. Yeah. Where did I stop here? Oh, I think it was here. Indicating that the structure encodes an IPFS URL scheme. This makes it agnostic in terms of which storage system is used. It could be changed in the future, or we could even get to choose which storage system we want the bytecode to reference upon compilation. To retrieve the metadata file, we would have to connect to the same swarm network through which the metadata file was uploaded to, using something like swarmgateways.net or setting up a local swarm node. Right now, this is something that is quite difficult to do because Swarm is still under heavy development and has not yet stabilized its hashing scheme, which can be seen is something being addressed by Solidity. Okay, I think I stopped in this one. Dasho hash itself is a specific hashing algorithm executed on the metadata file of a contract, which the Solidity compiler calculates after it has run all its other tasks, mainly compiling. Oh yeah, and if you're still there, what internship did you get into? And how hard was it? Because I'm thinking about, I think if I could choose, I would probably prefer to work on blockchain stuff. It's more related to things I'm interested in. I'm not sure exactly, yeah, if Ethereum is gonna be the thing, but I think the technology behind is really interesting. But Ethereum may not be the one that is the final one or the main one in the future. When we were trying to interpret these bytes as EVM opcodes, some of the hash bytes didn't have a corresponding opcode, and that's why we were getting invalids. In fact, a hash may just by chance produce any set of opcodes, which will make all hashes different and look weird when using tools like Remix. What I do is ignore the bytecode when I see a log1, followed by a push 6 and a few invalids. understanding that what I'm seeing is the metadata hash injection that the Solidity compiler makes. This concludes our analysis of this bizarre structure found at the end of every contract produced by Solidity. Better yet, this concludes the entire series. If you followed along and digested this considerable amount of highly technical, endlessly boring material, at least to most people, then I salute you. Hope that by now you feel right at home when you see EVM bytecode in the wild, and that you add this skill to your toolset when analyzing and developing smart contracts for Ethereum. Never worked with blockchain, but my Rust friends avoid it at all costs for some reason. It's just echo chambers, I think. And people in crypto are like that as well. A lot of people, they just defend mindlessly the stuff. Just tribal thinking. And probably the reason because this happens is because people want to save energy and minimize risks, so they want to be a part of the group, and if you present ideas that go against their identity, they have to reflect on their entire life, just so that people get invested in the ideas they believe in. And this generates gravitational force and makes people organize themselves into tribes. The only reason why I'm interested in, not the only reason, but the main reason I think, is because I think it makes sense to combine that with artificial intelligence. If you're gonna automate systems, I think it's gonna be related to, I think it might be a good way to try to achieve some equilibrium over the decision making of autonomous systems. Yeah. But like I said before, I don't like to think it this way. Like both with jobs and with money, I think is not a good idea to focus on money or jobs. It's more about focusing on the fundamental causes of that. So trying to understand better systems and that kind of stuff. But at the same time, I understand, like, money, salary is important. But yeah, there's much more to it, obviously. I started learning web dev this year. Generally, I have 9 years as a financial analyst. Internship is company that normally does SOW for the US government. I don't have any idea of SWE is. I think their biggest contract is with NASA. God damn, man. NASA. So they're probably genius. I start next month. The plan is to speak with the CEO to see if he would allow me to string. He created the blockchain curriculum. Oh yeah, that's another thing. A lot of companies don't like people to string because their stuff is not open source. He created the blockchain curriculum. I haven't seen the material yet, so I'm not sure if he would let me do it. But he said he would teach me what I needed to know, so he's not worried on my SWE blockchain exp. Software engineering, okay. I don't see how AI and blockchain are connected. He's working on a project and I think he accepted me because of my finance background. Yeah, man, NASA is pretty legit. The way that I think blockchain and AI are connected is because of the Internet of Things. The more things become automated, we're gonna need to have regulation systems that, because machines are gonna communicate with each other to make decisions because everything's gonna be connected, and artificial intelligence is gonna be integrated on that because we're gonna have autonomous agents that feed the data of the environment, which is pretty much machine learning. to make these decisions and to upgrade the state of the system as a whole. And that's what I think is gonna happen. That's why people have been implementing 5G, I think. And also because they want all your data and to control everyone. But that's beside the point. And when I say they, I'm not saying a specific. It's just the way that the system converges over time. Just a property of the market economy in a global scale. Once I figure out more information, I will be more than glad to share it with you. Awesome, man. Good stuff. But even if they don't let you stream, I'm pretty sure you can do it. Depends on the contract, I think. But maybe you can do it on your own time and you can just do your own thing. It doesn't need to be related to the stuff you're doing with them. I think I'll be right back. I should go to the bathroom. I think I'll do one more exercise. And then I'm probably gonna be done for today. Thought about doing that, do their curriculum the weekdays and possibly do my own thing. Yeah, but you have to look at the contracts. I didn't realize this before as well, but if you're working for a company, usually, especially in the tech space, some companies will not allow you to do your own thing. They will claim ownership of your intellectual property while you work at that with them if you build your own thing, but it really depends on the contract, so you have to look into that. Which makes some sense if you think about it, because obviously they don't want you working for them and then creating something to compete with them. That would be fucked, but at the same time it's kind of shitty, but yeah. But it should be possible to find a way, because people start their own business while working to someone else, so. But I'm also interested to know what you're gonna build, or this stuff you study. No problem. Because in this, the blockchain stuff is really interesting, but it's kind of hard to find a direction to explore, let's say. So far, the only thing that I thought about was investigating the transactions based on the blocks here, to see the connection between people and companies from the blockchain. But I didn't think about any other ideas of things that I can do as a project to put on my portfolio to increase the chances of getting hired. But I'm pretty sure I'll come up with something eventually. The median is the middle value in our ordered integer list. Find the median from data string. Find an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. Okay. So if the size is even, it's one plus the other. On the two middle values. Implement the median finder class, median finder initializes the median finder object. Voids a num int num, adds the integer num from the data string to the data structure. Double find median returns the median of all elements so far. Answer within 10 to the -5 of the actual answer will be accepted. I'm supposed to use a heap for this one. Not even sure. So let me search what is a heap. I think it's the stuff for the memory, but I don't know, in Python. Complete binary trees, in which each node is either smaller than or equal to, or greater than equal to all its children. Oh yeah, I think I remember now. Because you usually use for heap max and heap min. maximum or minimum problems. I think the order doesn't matter as well. I don't like the way that they did this description here. It's kind of hard to understand what they want me to do. Like, am I gonna receive a list? No, I'm positive that I can't do it, probably. But I'm just doing this to think about it. Like, my idea is just to run through the list as fast as I can. Like 20 minutes for each Initially it was 30 minutes, now I'm doing 20. Because I just want to see roughly how the problems are and what they ask and what's kind of the paradigm of thinking for each one. And then after I'm done with that, I'm keeping a mental note of the things that I'm struggling with. And then I'm gonna dive really deep into each topic, studying the stuff that I don't understand until I'm sure that I understand the patterns. I have a list here. This list that I found from this site, has the link here. So the first one that I'm thinking about focusing on is the 2 pointers one, because it is easier and high return on investment. And then I'm gonna do the trees and then graphs, probably, and then or linked lists. Hash I think is not that difficult from what I've seen, but I could be wrong. So the way that I like to do things is first go wide and superficial, and then once I understand the bigger picture, then I go deep and focus. I think that's the best. You combine the best of both worlds. And probably trees are gonna be the thing that I spend the most time with, because I suck at them. And I also suck at recursion as well. So I have to read about that a lot and study that a lot. But it usually seems like every one of these topics is a collection of patterns, and there's not that many patterns, so all you have to do is learn how each pattern works and then how to combine them. And then you have pretty much a basis for solving any problem. And it's more about, for me at least, it's more about trying to train myself to understand if I don't know which structure I'm gonna use, how can I look at a problem and understand which one is probably the best? Because I care about solving real problems, obviously, and not just these problems here. And I'm aware of this list here. People told me that is really similar to this one, so I decided to do this one. What's this book about? I got this book here recently. So I'm gonna read this book here, while I try to solve the problems in the Blind 75 list. Hopefully it will help me out. This is not a book. PhD thesis. Ah, interesting. At least the hash problems I've seen from this list are the easiest ones. Trees are the ones I found the hardest so far. Even tries, it seems a little bit easier than trees. And this one I have no idea what to do, so probably really hard as well. And I know dynamic programming is hard and graphs is hard. So imagine all the other ones are really hard as well. Well, it's sad on the one of the problems that is supposed to say like try with the RY. So yeah, but whatever, try. Prefix tree, this is the same thing. Hmm. How I assume you guys do these problems a lot, or at least you have a lot more experience than I do with data structures and algorithms. How relevant do you think it is when you're building real applications? Like how often do you use them, or not necessarily use them directly, but you recognize the patterns, or and solving the problems makes you better at building the applications, or thinking about the way that you're gonna build them? Really? So what's the main benefit of doing them? Yeah, so you do get better. Hmm. And it's still kind of hard for me to draw the line of how useful this actually is to my specific situation. And sometimes I feel like I don't want to spend energy trying to solve something that it doesn't matter, but I also feel like it can be helpful to understand more about computers and building applications in general. You usually need a solution for the main problem, not an abstract algorithm question. Yeah, I don't know. I guess the best way to know is to try to become at least reasonably good and then go back to trying to build applications and see how different I'm thinking. And if I sense that's not that useful, I'm probably gonna stop and just focus on building stuff. It's probably better. The main problems to solve is backend that boil down to simple CRUDs and relatively straightforward pre-post process of in and out coming data. Hmm. Yeah, so maybe that's what I should be focusing more, right? Until I get that stuff down and then I focus on the other stuff. I think I'm gonna look at the solution for this one. I have no idea how to do this. I don't even understand what he's asking or what I'm supposed to do, which direction to go. It depends on what you want to do. The main stuff is artificial intelligence and building things. I think though, there's a feel like artificial intelligence. It will definitely help me to understand better how this stuff works because it's pretty much matrix multiplication. So, and also from the blockchain stuff, I've seen some algorithms that use graphs and searching graphs. I've heard of by the name and some classes I watch, but yeah. So it probably is useful. Also for hacking as well, because of networks. I think I have decent math background, but depends on what you classify as decent. But for getting hired is obviously not the main focus. It's more long term. I can't be initializing a heap and then passing the numbers to the heap and then just finding the median of the heap. Can't be that easy. So it's probably something else that I don't know about. Yeah, so I'm just gonna look at the solution. It's probably about finding the root of a heap or searching the heap somehow and to get the value that you want. And imagine what the problem is about.
Okay, so today let's solve find median from a data stream. So this is another hard problem, but it's not super difficult if you know the data structure behind it. So they basically tell us we know the median is defined as the middle value in a sorted integer list. If the list is even, there is no middle value, so you take the average of the two middle values, right? So with this sorted array, the middle value is 3, so the median is 3. With this, there is no middle value, so you take the two middle values, add them together, divide by 2, and then you get a median of 2.5. And so we're actually designing a data structure that's going to have two operations. One operation is going to be adding a number to our data stream. So we actually have to store the list of numbers, and that list of numbers is not constant. It's going to be changing every time add number is called. And then from that list of numbers that we're going to be maintaining ourselves, we are going to need to constantly be finding the median of that list. So every time this function find median is called, we have to return what the median is from the elements so far. So this is just an example. If we add num1, then our list is going to have 1 in it. If we add another number 2, then our list is going to have 2 numbers. Then if we want to find the median, we will take the average of these two, and it's going to be 1.5. After that, we'll add another number 3, and then we'll find the median again. In this case, the median is different because our list got updated. The middle value is now 2. So what's the most obvious way to solve this problem? Well, I basically just hinted at it, right? So the obvious way to solve this is insert elements in order. So let's say these are the function calls that are going to be made. So we're going to add 4 numbers and then we're going to try to get the median. So we're going to maintain a list or an array, right? And every time we get a function call add 3, we're going to insert in order just like it says up here. And basically, if our array is always sorted, then it's going to be easy to identify the middle number, right? Which is going to be the median, right? So the median is always going to be in the middle position. And if our array is sorted, we'll always know where that is. So the first one we have is add 3. So just add it to the first spot. Next, we want to add 2. So how do we do that in order? Well, we have to traverse
traverse our array so far. So we see that there's a 3 over here, right? So then we got to replace that 3. We shift the 3 to the next position, and then we put a 2 in the position that the 3 was initially at, right? So now our array is in sorted order. We had to shift some elements, and we had to search for the spot that we put the 2 in, right? So you can tell that every time we add a number, it's going to be an O of n operation, where n is the number of elements we have added so far. So we added 2. Next, let's add 1. Well, we're going to traverse the array, right? We're going to see, okay, the first element is 2. We know that 1 is less than 2. So really what we're going to do is cross out the 2, cross out the 3, right? Shift the 2 over here, shift the 3 over here, and then put a 1 here. But I'll just, to keep the picture simple, I'm just going to put the 1 over here. But we know that in the worst case, every time we insert an element, it's going to be O of n. Lastly, we're going to take the 4 and add the 4. So we're going to see 1, nope, 4 is bigger than that, 2, nope, 4 is bigger than that, 3, nope, 4 is bigger than that. So we add the 4 at the end. So now we finally have a get median call. Well, good thing for us, since our array is in sorted order, we know getting the median is super easy. In this case, we have an even length list, right? We have 4 elements. So we are going to take the 2 middle elements, 2 and 3, add them together, divide by 2, we're going to get 2.5. So we know that the get median operation is always going to be O of 1, but adding a number is always going to be O of n. So how can we speed this O of n operation up? And let me just tell you, basically what we're going to do is, instead of having just a single list of elements, we're going to break this up into 2. And we're going to have basically 2 subsets, right? And 1 is always going to be less. So this has 1 and 2, and this has 3 and 4. And all elements from the left are always going to be less than or equal to all elements in the right. So this will also make it easy for us to get the median. But I'm not just going to have arrays. I'm going to use a heap or a priority queue. So we're going to use a heap data structure. So I'm going to have 2 heaps in this case, a small heap and a large heap. Small heap, all elements in the small heap are always going to be less than or equal to all elements in the large heap. Also, the size of these heaps is always going to be approximately equal. So if there were 2 elements in this heap, then there has to be 2 elements in this heap. What if we had an odd number of elements? So what if there were 3 elements in this heap? That's allowed because we know that we can't actually have these be equal if there's a 2 and a 3, right? Or in the opposite case, there could be 2 elements here and there could actually be 3 elements here. That's also allowed because we know that's approximately equal. If the difference though is ever greater than 1, so if there were 4 here and 2 here, we know then we have to balance them, right? Make this equal 3 and make this equal 3, right? We always have to keep it as balanced as possible. And if you're not familiar with what exactly a heap is, it's basically like a list. It's pretty similar to a list. It's implemented using arrays or lists. The only difference is, though, adding a number, we don't add at the beginning or at the end. We just add elements to the heap, and adding an element to this heap is always going to be a log n operation. And removing an element is also going to be a log n operation, right? So add or remove is log n. And there happen to be 2 kinds of heaps, a max heap or a min heap. And the thing about these is, so for a max heap, finding the max in this list, so find max in a max heap is always going to be O of 1. So that's the advantage. We know that finding the max in a regular list is O of n because you have to search the entire list, but with a heap, we can find the max in constant time. Similarly with a min heap, if you want to find the min, that's also an O of 1 operation. So with that being said, the small heap is going to be implemented as a max heap. And the reason we have a max heap and not a min heap is kind of counterintuitive, right? If this is the small heap, why are we using a max heap? And for this one, we're actually going to have a min heap instead of a max heap. And the reason is, what if we had elements to these heaps such as, right, what if we had these elements in each of the heaps, right? We see that all elements here are less than or equal to the elements in the right heap. But if you actually want to find the median of these, we know we need to get the max value in the small heap, right, 2, and we need to get the min value in the large heap, 3, add them together, and then divide by 2, right? That's how we're going to get the median. So that's why we need the min heap, right? We always want the minimum value from our large heap, and we always want the max value from our small heap. And of course, finding the median like this way, right, getting the value from each of the heaps, it only works if the size of the heaps is approximately the same, right? If in this case they're equal. But what if we had a third element in this heap? What if we had a 3? Well, they're approximately equal, right? But you can see the length of this one is greater, right? But the difference in length is 1, so they're approximately equal. In that case, how are we going to find the median? Well, since we know that the length of this heap is bigger than the length of this heap, we know that we have an odd number of elements in that case, right? If one heap is bigger than the other, there's always going to be an odd number. And in that case, we're going to want to get the value from this heap. So if the length of this heap is bigger, we're going to want to get the max from here. We're going to want to get the max value from this heap, and that's going to be 3. And we know in this case, 3 happens to be the median, right? Because look at them, these values are in sorted order. We get rid of these 2, we get rid of these 2, the middle value is 3. And I'm not going to walk you through this case, but let's just say, imagine we had a 2 over here. The exact same thing would happen, right? We would get the min value from here, we get the 2. And notice that, look, the max value from here and the min value from here are equal, right? That's why I say every value in here has to be less than or equal. It's possible that they are equal. Okay, so now let me just go through a quick walkthrough of this code again. So what we're going to do, add the first element, which is a 3. Which heap are we going to add it to? In this case, it doesn't really matter. So what I'm going to do is just by default add it to the small heap. So let's add 3 to the small heap. And we know that that was roughly a log n operation, right? Next, let's add 2. So by default, I'm always going to take whatever element we added, I'm going to take it and add it to the small heap. Now I added 2 to the small heap. But wait a minute, now the heaps are not approximately equal. This has a length of 2, this has a length of 0. It was okay when this had a length of 1 because that's still approximately equal, but 2 that's too big of a difference. So now what we're going to do is find the max value in this heap and add it to this heap, the large heap, which is always going to have elements greater than or equal to the small heap. So we need to get the max value from this heap, and since this is a max heap, actually finding the maximum is an O of 1 operation. Now the downside is we have to remove that value, which is a log n operation. And we're going to take that element that we removed and add it to the min heap, and that's also going to be a log n operation. We know adding and removing from heaps is always log n. Finding the maximum in a max heap is O of 1. Finding the minimum in a min heap is also O of 1. Okay, so now we did add 3, add 2. Now let's add 1. I'm going to change this add 1 to a add 7 just to illustrate one last thing about this algorithm that we're going to do. And let me just cross this out. We're not doing insert order anymore. We're doing the heap solution. So we're going to add 7, right? By default, I know that I'm adding it to the small heap. So what am I going to do? I'm going to take 7 and add it to the small heap. Now, the size of this heap is 2. The size of this heap is 1. So they are approximately equal. The last condition, though, is every element in the small heap less than or equal to every element in the min heap. Now, how are we going to check that? Well, we can find the minimum of the min heap in O of 1 time, right? It happens to be 3. We can find the max of the small heap in O of 1 time. It happens to be 7. Is 7 less than or equal to 3? No, it's not. So what are we going to do? Well, we're actually going to do the exact same thing we did before. So I'm going to find the max from the small heap in O of 1 time. I'm going to remove that max. So 7 is removed. To remove, we know it takes log n time. And then I'm going to add it to the min heap, which also takes log n time. So now I'm adding 7, and the lengths are approximately equal still, right? This has 1 element, this has 2 elements. And now if we get the maximum from here, 2, and we get the min from here, 3, we see that the condition actually now is true. Every element in the left is less than or equal to every element in the right. Now we added 7. Now let's do add 4. So by default, I'm always going to add it to the small heap. So I'm adding 4 to the small heap. The small heap has 2. The large heap has 2 also. But we know that this condition doesn't hold, right? The less than or equal condition. If we get the max from here, that's going to be 4. If we get the min from here, that's going to be 3. This is just not true, right? 4 is not less than or equal to 3. So we have to pop this, and we have to move it to this heap. So now everything is good, right? It's every value is less than or equal, right? This has 2, this has 3, that's less than or equal. Great. Only problem now is the lengths are not approximately equal. This has 1 element, this has 3 elements. So since the length of this one is greater, what are we going to do? We're going to find the min O of 1 time, remove that min, and then move it to this heap. So we know that the min is 3. We can do that in O of 1 time, but removing it is going to be log n, and adding it to the left heap is also going to be log n. So now the lengths are approximately equal. This has 2 elements, this has 2 elements. And the other condition, find the max from here, find the min here, we'll end up with 3 and 4, and less than or equal is definitely true. So it looks like a lot of work, and it definitely is. It's a lot harder than just having one array, right? It's definitely more code, but it's also a lot more efficient now. The only thing we have to do is get the median. And the time complexity for get median is actually still O of 1, which is exactly what we wanted. Let me show you why. Well, we need, in this case, we have an even number of elements, right? 2 plus 2 is even. So we want to find the maximum from our left heap, which is 3, right? We know we can do that in O of 1 time because this is a max heap. We want to find the minimum value from our right heap, and we know we can do that in O of 1 time because this is a min heap. And we know that 4 happens to be the min value. So we get these two values, 3 plus 4, add them together, divide by 2, and that's going to be our median. So we can still find the median in O of 1 time, which is great. Now, with all that being said, let me finally show you the code and show you that it's not as long as you might expect. Okay, so now let's look at the code. So here's a couple comments. We're gonna have 2 heaps, large and small. Large is gonna be a min heap, small is gonna be a max heap, and the heap should be roughly equal to roughly the same size. So in Python, you can actually have a heap be just a list, and I'll show you the other things we'll need to do later. So actually in Python, since these are members of this object, large and small, we need to have self as the prefix. And so now we have 2 functions to implement find median and add num. Let's start with add num. So just like I showed you, what I'm gonna do is I'm always gonna take num and add it to the small heap. So heap q.heap push. This is how you do it in Python. Other languages might be different, obviously. So to the small heap, we're going to push num. Now Python is kind of annoying in that it only implements min heaps. We know small is actually a max heap. So to get around that, what I'm going to have to do is take every number and actually multiply it by -1. This allows us to actually implement a max heap, which isn't implemented by default in Python for some reason. But what I'm doing here is taking num and adding it to the small heap, the max heap, right? But now we want to make sure every element in small is less than or equal to every element in large, right? So every element in the small heap has to be less than or equal to every element in the large heap. So I'm going to make sure that that's true. So if small and large are non-null, and so from our small heap, our max heap, what I'm going to do is get the max value from it. So how can I do that? I can just take the index of 0 because it's implemented as a list. Heaps are implemented as lists. So if you get the 0th index, you're getting the max value. We know that every time we add a value to the small heap, we're multiplying it by -1. So to reverse that, I'm going to take this value and multiply it by -1 and get the true value that we actually added to the heap. And so I want to know, is this value somehow greater than the smallest value in our large heap? How can I get the smallest value in our large heap? I can do the exact same thing, index of 0, but I didn't have to multiply this by -1 because this is a min heap, and that's what Python does by default. So if this condition is true, let me make it look a little nicer. So that mainly this condition is true, meaning that some value in our small heap is greater than our large heap, then we have to pop from our small heap and then add to our large heap. So I'm going to heap q.heap pop. So I'm going to pop from our small heap. I'm going to get the largest value from our small heap, store it in val, and then I'm going to push that value to our large heap. So to our large heap, I'm going to push that value. Basically exactly what I did in the picture, but maybe the code is a little confusing. Oh, and actually, since we know every value pushed to the small heap is being multiplied by -1, to reverse that, we have to also multiply by -1 when we pop from it. Because look, when we push to it, we multiplied that number by -1, but to our large heap, we can actually give the correct values. We don't have to multiply by -1. That is actually probably one of the more confusing parts about this, which is annoying because there's no way to really get around it in Python. So now we check this condition. The only other condition that we have to check is what if the size is uneven? And so by uneven size, we actually mean a difference greater than 1. So if the length of small is greater than the length of large plus 1, that means the difference is 2 or greater. In that case, what are we going to do? This is too big. So what we're going to do is pop from the small and then push to the large, which is actually exactly what we did up here. So I'm just going to copy and paste that. And the other case is if the length of the large heap is greater than the length of the small heap plus 1, meaning the difference is 2 or greater. And in that case, I'm basically going to do the opposite of what we just did up here. So let me copy and paste that. So we don't need this -1 because we are going to be popping from the large heap, which has the correct values, not the -1 multiplied values. And with that value, though, I'm going to take that value and add it to the small heap. And actually, we are going to need to take this value and then multiply it by -1 because we have to do that whenever we add to this small heap. So now we are making sure we take every element, add it to one of the heaps. And if there happens to be a size difference, we are handling that. If there happens to be an order difference, right, like the values are in the wrong order, we're handling that as well. And remember, all of these heap operations are log n operations, log n. And now the last thing we have to handle is finding the median. So one case is that there's an odd length. How do we know if there's an odd length? Well, if the length of small was ever greater than the length of large, we know that then we have an odd length, right? Because maybe one of them has 3 elements, the other has 2 elements. We know with this function, we're always making sure that they're about roughly equal. So if this evaluated true, that means we have an odd number of elements, and small happens to have an extra element. So what we can do is return the largest value in small, which is stored in index 0 of small. If the opposite is true, if the length of large is somehow greater than the length of small, we know that the opposite happens to be true, so we can return the smallest value in large. Now, if neither of these evaluates, that means we have an even number of elements, so each of these heaps has the exact same size. So what we can do in that case is return the largest value in the small heap plus the smallest value in the large heap, add them together, and then divide by 2, and then return the result of that. So here is the final code. It's 34 lines, but you can see we have some comments and some, boilerplate type code. But the code itself that we had to write was relatively short, right? Because we did this with a heap and we did it pretty efficiently. Let me just run it to prove that it works. Okay, just one time I forgot to say that this small is a member object, so self.small, and I actually forgot to do that in a couple places. So let me just fix that. So self.small, self.large, self.small, self.large, self.small, self.large, and a couple more places. Okay, so we corrected the self errors. One last thing I forgot is remember small as negative. We multiply the numbers by negative, so when we're getting the number and actually trying to calculate the median, we have to take that number and multiply it by -1 before we add it to this number and then divide by 2. And let me not forget to do the exact same calculation when we're returning the value here, right? So I somehow had too many bugs in here, but okay, so now finally, this should be the final code. The big thing in Python at least is to remember these -1s. If you're doing this in C++ or Java, I'm pretty sure you will not have to worry about that. This should be the final code finally, and you can see, yes, it is pretty efficient. And in Python at least, it's not a lot of code. I think even in Java and C++, it shouldn't be that much code either. So I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Okay, so I think I'm gonna stop here. Continue to do this tomorrow probably until I'm done, and I'll probably end up focusing on 2 pointers first, then maybe linked lists because they are easier, and then trees and graphs then. Alright, see you then.